So good morning. I'm Zoltán, as Thilo kindly introduced me. And the idea of me starting with microscopy is that, in our experience, we have been teaching this for a long time now. If you don't have a basic understanding, really of advanced understanding of microscopy, then on the one hand, designing your experiments will not be done optimally, or you will rely on help from somebody who may not know your biology. And the data that you generate or you receive from a colleague who generated the data for image analysis will not be adequate, will not be so, let's say, good enough for analysis, and definitely will not be optimal. And why is that? It is because we have certain requirements that we need to satisfy, or at least need to know about, so that we can design our entire experimental pathway from designing the biology to carrying out this is coming up, carrying out the labeling. Perfect. Sometimes we just got it right to the distance. We need to do that. But and this means that the whole project will suffer. There have been cases, for example, when, as you know, our department is solely involved in image analysis and modeling. We do not per se do microscopy. I am the one who goes with collaborators and helps them to set up microscopy so it is done as optimally as possible. But this also means that if you don't satisfy you don't take advantage of your microscopy setup, then you are delaying your project. And like I said, we have cases where someone came with a set of data which were really not adequate for analysis, and then we ask, okay, can you redo them? No, because the PhD student graduated or the master student graduated, she is gone, the cannot be done. And then we do our best. And you will also learn in these 3 hours how you can improve things so you don't have to be optimal all the time. You can compromise, but it's also important to know where you can compromise, where you should compromise, depending on what you want to get out of your imaging data. So it's not programming, it's not image analysis, but it's a basis for image analysis. And here you just see a list of points that we have experienced in many years that we have been doing this kind of job that I briefly summarized earlier. So there is your responsibility as an image analyst, and then there is the biologist's responsibility. And our idea with JIPipe was, as Thilo explained, that you would be the same person for both tasks, take your microscopy data, but also be able to get quantitative information out of the data. And this is very important, not only because then you don't always rely on somebody else's help, but also because you will see this. You design your experiments differently once you know exactly what is going to happen to your data. And then you will say, okay, I am going to resolve my nuclei, so my resolution has to be such and such, but I also want to see actin filaments, so my resolution should be higher, because I learned, I know that otherwise I will not be able to quantify them, I will not be able to measure the length of the actin filaments, and so on and so forth. But if you are only looking for nuclei, you will also know, okay, I don't need to see 100 nanometer detail because it's a big object, it's a big nucleus. Why bother? Why waste my time, energy, labor, and money when I don't need it? And it's also very important that you share the responsibility. If you are the same person, doesn't matter. But if you are working with a biologist or if you are working with an analyst, you share the responsibilities. You cannot be, oh, this data is crap, I cannot live with that. You have to give feedback, and if it's your own data, you have to know from the beginning. Okay, So how do we build up such a knowledge that helps us get the best out of microscopy? These are the basic points that you need to know, and we will go through them one by one, and we will end up here where you will hear more about this afternoon, tomorrow, and again on Wednesday, the image analysis part. So let's start with one of my favorite subjects, or way to show this is the pyramid of frustration, as they call it. It is basically what I mentioned, that you have to compromise. You will not be able to get the absolute perfect image in reality. In theory, of course, in reality, you cannot. These are the main concerns that you will have during your microscope experiments. You need to protect your sample. If it's a live sample, it should stay alive. If it's a labeled sample, it should not lose the labeling, as it is called. It should not bleach during the experiment. Your resolution should match your demands and your, how good the images are. The signal to noise ratio has to be high enough for whatever your purpose is. Again, measuring purely nuclei doesn't need as high a quality of an image as measuring active filaments. And the acquisition speed, how fast you collect images. It's especially important, of course, if you are working with live samples, partially because you don't want to expose them to laser light longer than you have to. And also because they might be moving. For example, you are measuring phagocytosis and then you want to see the filaments reaching out, grabbing the bacteria, and you need a certain speed, otherwise you miss the whole thing. And last but not least, you cannot set up an experiment which lasts 24 hours like a microscope. So you need a special place where you are allowed to do that. So you also want to limit how long the experiment actually takes. And you may want to go home at some point too. So for this one, you have to choose your priorities. For example, if it's a sensitive sample, live images, for example, like macrophages, we do mostly immunology, so I will bring my example mostly from that field. You may want to protect the sample so they don't die, and you need to acquire fastly because they are active. In this case, in this pyramid, where the four corners represent these four concerns, you have to choose an area where your temporal resolution is high, so you are close to this corner, and your specimen health is taken into account, so you are close to this corner, but you don't care about the other two corners, the spatial resolution and the contrast. Again, for example, I'm tracking nuclei. I need to get the data quickly, but I'm not tracking active filaments. Or it's the opposite. I have a labeled stained label, a labeled sample, fixed, so I need to resolve molecular clusters. I need to resolve, for example, nanoparticles, bacteria inside macrophages. Then I need the resolution, and I need the signal to noise ratio because I want to count individual bacteria. In this case, I'm on a different plane in this pyramid. Now, with the advent of AI and AI-based image analysis models and tools, the requisite on the signal to noise ratio has been eased a lot because I can afterwards train a model that learns on high resolution, high signal to noise ratio images. And once you train that model, you can use lower signal to noise ratio images to predict what this image would look like had it been done at a higher signal to noise ratio. So we enjoy a little bit of requirements on this corner with AI. And then these are the requirements that we need then for imaging. And I will try to go through these as quickly as possible in the next 2.5 or so hours. I need to teach you a little bit about the basics of optical, geometrical optics to understand how a microscope works, which will then later help you to set it up, to know exactly what the microscope can do, how should I set it up, and why should I do it that way. I try to be not too detailed, but enough so that you understand a little bit more when you leave here on Wednesday. So basically, the principle behind why we can do microscopy, we can do lenses, we can build cameras, is based on the phenomenon of refraction. Refraction means that when light arrives at the border of two different mediums, for example, air and water, or air and glass, it changes its direction of movement. So if there was a light beam, for example, a laser light, arrives at the surface of, let's say, air and water, it will bend towards this perpendicular vector called the normal vector. So this angle, the incident, is larger than the reflection. That's called refraction, and the ratio between these two angles is not random. It is determined by this law, which says that the sine function of this angle divided by the sine function of that angle is a constant that's characteristic to the pair of the media. For example, this number is 1.33 between air and water. It's 1.5 between air and glass. And it would be 1.5 divided by 1.3 between water and glass. So if you know the n, the so-called refractive index for the two materials, you can also calculate their relative refractive index by dividing these two numbers. So this means that when light comes from air to glass, it will bend more than if it were coming from water to glass. And if it comes from glass to glass, it's not going to bend. And this will be important later when we learn about microscopy and how to reduce the distortions caused by the microscope itself. You can demonstrate this very simply. You take a half disc of plexiglass illuminated with a laser, and you will see that this angle is larger than that. There is also a second beam here that you will see. That's a reflecting beam. The reflection occurs at the same border that you see, and the law here is simply that this angle equals that angle. This is also true for mechanical motion. If you play billiards, you will notice that unless you put a spin on the cue ball, it will bounce the same angle. If the table is a good table. So what happens when I illuminate a piece of glass with such a light beam? Well, it will bend when it enters the glass. But then what happens when it exits the glass? Well, it should bend, it's reversible, so it now will bend away. But the same law applies, that the sine function of this R and the sine function of this I will be again the reflective index, but the inverse of it. So when I have a piece of glass like the window pane here, the light will just shift. It will not bend at the very end, because what it bent at the entrance, it will bend it back after the exit. So this means that with a piece of flat glass, I cannot really do much in terms of directing my light around. So what I need is a different shape. But before we go there, one consequence I wanted to call your attention to is that when the light exits a higher refractive index material, which we can call optically more dense, because the N is above 1. For example, it exits from glass to water, or from glass to air. It will bend away, as I mentioned. But that also means that there is an incoming angle at which the exit angle is 90 degrees. That's called the total reflection, because above this angle, the light will simply not be able to exit the optically more dense material. So if I illuminate a piece of glass from inside, then some of the light will not be able to exit the glass. It will get stuck inside. You can also demonstrate this with a piece of laser. So as you increase the incoming angle, eventually you get to a point where you get a complete reflection. The law that describes this is obvious. The sine function of 90 degrees is 1. So the refractive index can be calculated by this function, where this angle at which this happens, the 90 degree gap, is called the critical angle. Since sine function is never above 1, this value is always above 1. You can demonstrate it the same way as we did before. So this means that if you are snorkeling and you look up, you are in water and you are looking towards the air, you will have light beams which are at or above the total reflection angle. So you will see that the ocean surface serves as a mirror because of that. So the turtle can see itself if it turns its neck. So because of that, there is a super resolution technique which we may or may not have time to talk about, which is based on total internal reflection. But even more importantly, and in everyday life as well, this is how fiber optics is built. So the idea is you make a cylindrical shaped piece of glass, you illuminate it from the end with a laser, and then you will now know that some of those light beams will enter the tube or the filament at an angle so that they will have total internal reflection. So you illuminate, and those at a high enough angle will simply bounce around. And since it's reflection, the angle is always the same. So if you got stuck once, you got stuck forever. And based on that, you can build cables, optical cables on a glass fiber, which will lend or which will drive the light from point A to B without illuminating the environment. Light is stuck. Of course, in real life, the structure is much more complex, but the principle is the same. Why do we need that? We need that because, for example, in a microscope, I want to use lasers for illumination. Do I want my laser being traveled across the room until it gets from the laser to the sample or not? So I want it to go directly from the laser to the objective lens to the sample to illuminate my cells, my nuclei. So I will use optical fibers to lead the light from it. And so your internet connection nowadays is running through optical cables. So back to my point about a piece of flat glass not doing much useful for us. We saw that light will simply shift at the end. So what do I need if I want to modify the light? Well, I have to use a surface between the two media which is not flat. For example, a water glass. The surface is circular, and if you see through this, you will see that the pattern behind it is distorted. Why? It is because the light that entered from the air to the glass, and then glass to water, and then water to glass, and then glass to air. This is how you see through a piece of water glass. Because of the curved surface, did not just result a shift. It resulted in a real refraction. And you will also notice that the higher the curvature, that is the smaller the glass, the more this refraction is, because of the law that we learned about. So now we have an idea. We can make a lens, named simply based on the shape that it forms. And then, if I have made a piece of glass which is surrounded by, for example, spherical or at least curved surfaces, then illuminating it with a light beam will result in the light beam bending, reflecting, and eventually meeting at one point. So what I can do is I can take, for example, the sunlight, which is pretty much a parallel light beam, it's sun so far, and I put, if you are wearing glasses, your eyeglasses in the light path or sunbeam coming through the window, then you will see that the sunbeam, which was originally the size of your sunglasses or your reading glasses or the long distance glasses, will be concentrated in one point. The phenomenon called focusing. So such a surface bound piece of glass will focus light. This also means that the energy that comes in this parallel light beam will be concentrated into a very small surface, a very small point. So this also means, I don't know if you guys play this when you were kids, if you take glasses and you illuminate it in the sun in the summer, and you shine this focused beam on a piece of paper, it will catch fire. Or if you shine it on your hand, then it will burn your hand. So the energy is constant. And this will be a critical point in microscopy when we go back to protecting cell health. Lasers are carrying relatively high energy, and if you focus a laser beam, when you shine that onto a cell, it won't light. It's too much energy concentrated. So that's why we will try to minimize the exposure time. Now lenses come in a million different sizes and shapes. They do not have to have two outside curving or so-called convex surfaces. They can have one convex, one flat, two convexes but set up as a meniscus, and so on and so forth. The simplest application of this is to use a loupe with a magnifying glass. Typical book cover for Sherlock Holmes book, where he can then magnify certain objects, and we will look at it why it magnifies. But if you are a stamp collector, then you have so how these magnifying glasses work, or some of the shopping carts in shops to have the older people have a magnifying glass attached to their shopping cart. Why is that? Why does it work as a magnifier? And if it works as a magnifier, then I'll build a microscope out. And how? And this is the principle that you have to remember, that the basic, very simple set of laws of how to draw an image formed by such a lens is the following. If you have an object, and we assume that it's sitting on the midline that goes through the center of the lens, that's called the optical axis, which we also important in microscopy, of course. And we set up an object, then any light that comes and goes through the center of the lens, we are talking about geometrical objects, so we are simplifying a lot, but the principles are the same. If the light goes through the center of the lens, it will not change its angle. We understand this because if the lens is very thin, then it's basically a flat piece of glass. And we learned at the beginning of the lecture that a flat piece of glass will not refract the beam, it just shifts it a little. The thinner the glass, the less it shifts. So an infinitely thin lens will not shift it, it just lets it go. So the beam that goes through the center and comes from the top of the object will go through the center. Now I'm observing it from this side. I'm a stamp collector and I'm trying to see what edition my stamp is. Also, we saw in the previous slide that a parallel light beam will be focused in the focal point. So the light beam that comes from the top of the object and goes parallel, what we now know called the optical axis, will be bent, will be refracted, so it goes through the focal point, the point where the light will be collected if the light beam is parallel. So I will mark my focal point, and I will draw this line which goes parallel, so it goes through this point. So now I know that these two lines will be the ones with which I can then now draw what my image is going to have. Now, as you see, these are diverging. They are not converging, they are diverging. So if I put a piece of paper here, I will not see an image. But if I put my eyes there, my eyes are basically lenses. More complex ones, but still curved surface objects which are filled with pretty much water. My eyes will then collect these lights, and they will see them as if the light, my brain will see it as if the light beam was continuing. And then when you continue these two light beams with the dotted lines, you will find a meeting point. And where these extended lines meet, this is the top of the image. So now I know that the image of this object is that dotted line arrow. So what do I see here? What I see here is that with this very simple object, a lens, I can magnify this object to this. What is this? 2.5 times bigger image. So if I look at the stamp, it is 1 centimeter. Now it looks like 2.5 centimeters. What I also see is that what was the top of the object is the top of the image. So the image will not be upside down. The image will be correctly oriented. And what I also realize is that this is a so-called virtual image. Why? Because what I said, if I put a piece of paper or a screen here, I will not see an image. It's not formed by the matching of the light beams. It's only formed because I'm looking at it with a second lens or with my eyeball. The same principle is true for lenses which are formed by concave surfaces. The same principle is true, except that the light beam which goes parallel to the optical axis will bend as if it was coming from the focal point. It will diverge. And the light beam that goes through the center will go undisturbed as we go. So this means that using such a lens, I can also form an image. If this is my object, and I draw my things as I did before, then I will get again a virtual image because the image is on the same side as the object. But this also means that I can combine these lenses. I can make more than one and then magnify the image further. Now, is there a law that covers where exactly the image appears and how big it is? Yes. You don't have to draw this every time you want to know this. This is the law. This means that the inverted value of the focal distance, which is the distance from the lens to the focal point, equals the inverted distances of the object from the lens plus the image from the lens. And from this equation, you can very simply, for example, calculate where the image is formed. If you know the focal point or the focal distance of the lens, and you know where you put your object. This means, of course, that I can also calculate the magnification, which is because of the simple trigonometry of the orientation. That the magnification will be the distance of the image from the lens divided by the distance of the image. So what does this mean? This means that my magnification will depend on where the object is relative to the lens. So when I build a microscope, I will want to have the focal distance of that objective lens that sits on the microscope designed such that this distance is short, so I can push the object close to the lens. This will have other advantages. And I want this focal distance also to be short. If I'm building a telescope and I want to look at the moon, then it's the opposite. You have to have longer focal distances. But if you have a camera with a teleobjective lens, the focal distance when you look at the markings, you say 300 millimeters, for example. That works to take picture of the Vienna Tower from here, but it will not work as an objective lens because the focal distance is too long. So what happens when I put two lenses next to each other? Very simple. I take the object, I calculate where the first image is generated. And then I consider this first image, the intermediate image as it's called, as the object for the second lens. And if you follow these lines in your free time, you will realize that putting two lenses next to each other, I will have an even higher magnification of the object. In this case, at the end, the image will be upside down, so-called inverted image. So when you look in a microscope, for example, you will realize that if you know which way your sample is oriented, that when you look at the image through the screen, the computer screen on a confocal microscope, it is going to be upside down. But indeed, it doesn't matter. It will be magnified, and in this case, it will be a real image. And this means that what I did was, using two simple lenses, I built a device which magnifies an object to as much as I want, basically, by setting the proper focal distances. So what I did was, I built a microscope. All of the microscopes that you will work are built on this principle. These are very simple principles. But if you understand this, then you basically know how your microscope works, even though a confocal microscope will cost you $500,000 to €1 million. But the principle behind it is still very simple. It's like a car, the pistons are the heart of it. That's what produces the power. But you don't pay for the pistons, you pay the whole thing that's built around to make it into a car. So with the microscope, you also don't pay for just the lenses, which cost you, I don't know, €10,000, but the stuff that's around. Now, this is very good. Now we know how an optimal, ideal lens works, but lenses are not ideal. They have aberrations. They cause distortions of the image. And we will go through only the very few of them that you need to know about. First of all, spherical aberration. When I told you how to draw the formation of an image, and I said light beam that comes parallel with the optical axis will be focused from the focal point, that is obviously not true, because the farther you are from the center of the lens, the higher the angle at which the parallel beam will hit the surface. So this means that light beams which come at the center of the lens will go undisturbed, but the further you go, the closer the focal point is. So a realistic light beam will not be focused in one focal point, but in a focal line that sits on the optical axis. And this means that when you look through a microscope using an objective lens which is not compensating for this problem, for the spherical aberration, then what you will see is that the center is sharp, but the further you go out, the less sharp it is. And you may have experienced this with real microscopes, that even with compensated lenses, that the edge of the image will be a little bit less sharp than the center. And the reason for that is that, how do you compensate for it? You simply change the shape of the surface so that every light beam goes through the same distance inside the lens. So it's going to look funny. It's going to look asymmetrical, but the advantage is that now you have 1/3 of one meter of the shot. So it's very easy to compensate for spherical aberration. And the lenses that you buy with your confocal microscope or even fluorescence microscope, they are compensated for such. Another thing which is oftentimes compensated for, at least for a range, is chromatic aberration. This is a very simple phenomenon. The refractive index depends on the color of the light. And this is because the refractive index is determined by how fast light is traveling in the medium, and the speed of light depends on the optical density of the material. Light travels at 300,000 kilometers a second in air, or nothing, in vacuum. But in water, it travels at 1.33 times slower. and in glass it travels 1.5 times slower. But because of that, the focal distance depends on the color. Blue light is focused closer than red light. But that's a big problem for biologists because then you say, my nuclei are here, and my active fibers are here, and my endoplasmic reticulum or mitochondria particles are here. I labeled one in blue, the other one in red, and I need to know are these mitochondrial particles traveling along the active fiber, which makes it more sense. It doesn't matter. Point is, I want to see if they overlap. But if I have this phenomenon, I cannot say if they overlap, because they will not overlap even if they do in reality, because the lens has chromatic aberration. So because of that, when you set up your microscope, when you set up your first experiments, especially when you're using high resolution micrometer or so object size, then you must check your images for chromatic aberration. That's the first step you have to do. You have to assume that spherical aberration is correct, if not, you can do about it. But this one you can, because if you measure the chromatic aberration, you can compensate for present image analysis step. It's not all lost if there is a chromatic shift. If you have to know it. How do you measure it? You take a artificial object like a piece of plastic, piece of polymer. It is perfectly spherical. You can buy these things. These are called beads, fluorescent beads. And these plastic particles can be stained with different colors: blue, green, yellow, red, whatever. Maximum 4 colors. And if you buy such a 4-colored bead, one brand is called Tetraspac, so 4 colors balls, and they are from 1 back. So the smallest one you can buy is like 100 nanometers, the biggest one is like 4 micrometers. If you buy a 4 micrometer one, you can easily find it in your microscope. And then you take an image with the different colors that you will use for your biological sample, and you check in your image, do the 4 different images, blue, green, red, etc. Do they overlap or not? You do it in 3D, so you also see the axial shift. And if they don't, then you will at least know that my focal point in blue is a micrometer away from my focal point in red. So if I see in my images that my actin and my mitochondria are micron apart, then I know that they actually do overlap. Now this can be compensated for up to a point according to this arrangement and this formula, which manufacturers do. You will see a bit of a real lens very soon. It's called an achromatic lens, but this is strictly only possible in this case for these 2 particular wavelengths. So for example, you can buy a lens which is compensated for red and blue. That's pretty good because those are the farthest wavelengths you will use anyway. So between green and yellow, for example, it's going to work quite well as well. This you will see on the labeling of the lens, which we will talk about in a minute. And a couple of them just on the level of mentioning. Coma aberration will mean that the focal point depends on not only how far you are from the optical axis, but also on the angle at which the light arrives at the lens. If you are not using a parallel beam, a microscope will do, then the different angles will result in different focal points in space, not just along the optical axis. So now a dot will look like a comet, hence the name coma. They look like little comets in the sky. The farther you are, of course, from the center of the image, the worse it gets. If you see this, then you have a problem, because then your lens, something happened to your lens. This should not be quite obvious, but if you see this, you will know what this means, and this makes analysis very difficult, because then you have to find these central points of the lens. And finally, astigmatism. This basically means that the focal point, the location of the focal point depends on not only of those things that we talked about, but also on the polarization of the light, the polarization angle of the light. This means that light that reflects from surfaces, you probably know that the light that reflects from water, for example, is polarized. The angle will depend on the polarization angle. So this means that reflected light, if you have astigmatism, will appear as these almost coma-like, extended, like spaceship-like structures instead of dots. So if you have a normal eye, for example, this is what you see in a city on a rainy evening. But if you have astigmatism, that's what you will see. And those of you who wear glasses and it's compensated for astigmatism, if you put them off at night, this is what you will see. If you put them back on, then that's what you will see. And a lot of people do have astigmatism in their eyes. And that's actually the reason for that. So that's the four basic aberrations. They can be compensated for also afterwards to some extent. They can be described mathematically. I will not go into that when we teach a whole semester class. We do learn about that, but today we don't have time. But there is a mathematical formula, the so-called Zernicke polynomials, that describe all of these aberrations mathematically, which means that in an iterative method you can try to compensate for them, try to estimate how much of these four problems you have in your image, and iteratively try to compensate for them. And it's possible, like I said, because there is a formula that describes all these aberrations. Another problem that ruins your images is scattering, light scattering. This basically means that when the photon, the light arrives at either at a small, like nanometer size object, for example, molecules, individual molecules or clusters of molecules, or something larger, like 100 nanometer or micrometer size, like dust particles, it will not continue straight. It will scatter in space. So, for example, if light arrives at a small object, very small object, and I mean nanometer size, again, single molecule size, instead of going straight, it will scatter not only forward but backward. And this is a typical scattering pattern for such small objects. The condition is that the size of the scattering object is much smaller than the wave. And you will learn soon that the typical wavelength for fluorescence microscopy that we use in visible light is a few hundred nanometers. So this type of scattering, called the Rayleigh scattering, occurs when your object is a few nanometers in size. It's a symmetrical pattern, looks like a number 8, a little bit on a baby biscuit. And this can be mathematically described. So again, if you know that you have molecules, that lipid molecules distributed like your imaging river, and you have a lot of fat, you can try to compensate afterwards by calculating the scattering pattern using the Rayleigh scattering formula, and then trying to calculate back what the image would look like without the scattering. If the object is bigger, like wavelength size, a few hundred nanometers, then it switches to the so-called Mie scattering pattern, which is more forward than backward. Asymmetrical, pointing forward, and the larger the particle, the more pointed it is. The formula for the Rayleigh scattering, in no ways you should know this, but this is what you would use to actually program formula that you would try to use to calculate back what the image would look like without that. And what you will notice is that the d is the diameter of the scattering object, so like 2 nanometers for a molecule. It depends on the 6th power of the diameter. So it's extremely sensitive to the size of the object. And this is actually useful because you can turn this into a measuring device where you actually illuminate your molecules distributed in a colloid solution with a laser, and you measure the scattering pattern. And you can then calculate the diameter of the molecules. Or you take nanoparticles to deliver drugs to kidney or liver or whatever, and you want to know the size of the nanoparticle. Instead of looking through a microscope to 100 nanoparticles, you dissolve them in a colloid and you innovate it with a laser and you measure the scattering method. And from that you can calculate the diameter. And if you calculate what it looks like, I just did this on a computer, when I assumed that we had, I think it was a 4 nanometer object and radius scattering occurred. If I illuminate this object and I look from half a micron apart, it's really not that far, that's much smaller than the size, the thickness of a cell. I already don't see the actual spot, I just see larger and larger scattered spheres. And this is still only 1 micron apart, this is 3 microns apart. So by the time you look through a cell, which is let's say 5 to 10 microns thick, the molecule that is positive will cause so much scattering that you will have no idea how big that molecule was. So besides resolution measures, scattering itself will cause you enough problems not to be able to resolve such large objects. And if you are 50 microns away, then you can forget it. There is no information left at all about the object. So this is the theory. Now let's see how we actually build such a microscope lens. And when you look at one, how can you get information about how this lens behaves without having to do measurements of your own? That is, we will look at lens properties and how to read them off the lens. This is what your objective is. That's screwed into your microscope. And before you start your experiment, you have to know what your lens is capable of. This will determine everything that you can make it do. Once again, like we talked about the engines, this is the main part, around which you draw the lines. If the lens cannot do it, no matter how expensive microscope we have behind it, we cannot. And most of these we will talk about, but briefly I wanted to go through that. So first of all, you have who made the lens, of course. And these are the values, or this is the information which will tell you what optical aberrations this has been corrected. And these things, when you read it from the lens, you go and Google it, or you go to the Zeiss website, for example, and you check out how much compensation you actually did. But for example, this will mean that you compensated for spherical aberration that you expect to be. This can also mean that for chromatic aberration, it has been compensated for, and then from the color of these colors, you can read out exactly which wavelength range it was designed. You will have the magnification. For example, this is the 63x. This is a very typical one. We don't know how to create 600, but size lens is usually have. We have 10, 20, 40, 60, and 100 typical steps. What does this mean when you look at, for example, a 1 micrometer size object with a microscope? Do you see 63 micrometers? No. Why? Because the microscope contains a second lens. You saw this when we marked this as the ocular. This is the lens that you look through. This adds an additional typically 10x magnification. So when I have a 63x objective lens, and I have a 10x ocular lens through which I look, then my total magnification will be the multiplication. So 600 by 30. So now that makes sense. Then 1 micron will look like half a millimeter. And then I can work with that. I can put this on a camera, take a picture of it, and then I can analyze. The next number that you always have to know, the numerical aperture. That is behind the dash, the forward slash. We will talk about it in a minute. This determines the resolution of the object. The higher this number, the smaller objects you can see. The rule of thumb is that if you take the wavelength of the light that your laser produces, for example, 400 nanometers blue light, and you divide this by twice this number, so 400 divided by 2.6, that will be the smallest object that you can see with this objective lens as a single thing. Anything above that will be appearing larger than it actually is, or if you have two objects which are closer than this distance, you will see them as one. So your resolution is determined by this number. The next letter, or combination of letters, in this case, differential interference contrast. It could also be pH for phase contrast, means what transmitted light microscopy modality is the lens prepared for. We will talk about this a bit later. This is prepared for differential interference contrast. This is a method with which you can see very thin lens, very thin cells, which you would otherwise not see with a regular transmitted light microscope. The next combination of letters IMM means it's an immersion lens. This means, and you will see why, that the lens, between the tip of the lens, this part of the lens and the sample carrier, the cover slip, for example, there has to be some liquid. And this liquid depends on the other labeling. For example, in this case, this liquid can be glycerol, it can be water, and if I turn this lens around in the back, it would say oil. So you can have three different kinds of liquids between the lens and the cover slip. Not all lenses have this opportunity to have all three. Most of them offer you either water, or oil, or glycerol. This also means that if you do not use the proper liquid between the lens and the cover slip, you will not get the maximum ability of the lens. What I mean is that the lens will still work, you will still have an image. But the numerical aperture, which, as you remember, determines the resolution, how good the lens is, will drop. Instead of 1.3, it will be, I don't know, 0.8. So it's important to check this label and then check what immersion it is designed for and use the proper immersion. And we will see why. This one indicates what correction it has been designed for. You have to look this up depending on the lens. Now, this number means that, without going into details, it's a so-called infinity correction lens. That's the symbol. In microscope design, if you go to the Optics Museum here in Jena, you will see that the old size microscopes, when you focus with the microscope, the size of the microscope will change. The length, the distance between the ocular and the objective lens to change. In modern microscopes, when you focus, you don't have to stand up when you focus away. Microscope going move. And that's because, to put it simply, and that's because there's an extra lens, the so-called tube lens, inside the light lens, which will make the light beam parallel inside the microscope. And I did mention this at the beginning that light beams in reality in a microscope are always parallel. And that's because of the tube lens. And without details, the point is that if you have a parallel light beam and you want to focus that light beam with the lens with which you focus can be anywhere along the light path, because the light path is parallel. So this means that when I focus, I don't have to move my lens according to the focal point, according to where the object is. But if I don't make this parallel, then of course I have to match the focal point. So I have to move the lenses away or closer to each other. So in order to avoid that, we use tube lenses. But if your microscope has a tube lens, then you must have a lens which has this infinity symbol. Otherwise, you will damage your lens. Because mechanically, they are designed. And I had seen this happen in my core facility. But this also means that if I have this symbol, then I can put this lens onto another microscope, which is also infinity connected. So if you have a size microscope for such and such, and you have a size microscope with better, you can give your lens to her, and she can put it on and to work. If it doesn't have the symbol, do not work. Don't try it. It even works between different companies, like Micron, size, Micron. If they have the symbol. Yeah. Yeah. Any question actually, by the way. Yeah.
In the past, I used to always buy cover slip for objective of 1.5 each, always.
Yeah.
But thinking that I mean, should I look is at this point my objective can have 0.17.
Yeah, we will get to that.
What happens if I'm not using this?
You
have some aberration.
Yeah, exactly. You will have spherical aberration because it's not corrected for that. So it's corrected for the 1.5 composite 270 micrometers. It will work, but it will not be optimal. And again, you are on from the prism of the pyramid. Yes, you are compromising because that's the length you have. But that's the color scheme you have.
But it's something, in any case, it's something that they can be, I mean, looking at that, I can realize that there is something wrong.
Yeah. You will see, like I said, so for example, the edge of the image will be much more blurred than the side. No? And we'll add it. Okay, so this is that. And this is what we just talked about, this range. In biology, naturally, you have a microscope sliding your sample on it, and a cover slip. A cover slip will shift the light. It will not bend it, as you remember what you shift it. Now, you remember also that if I shift the light will not use the optical axis, I will get spherical aberration. My lens is corrected for spherical aberration, but needs to know how much glass there is in between that. And this means that if I put a cover slip between myself and the objective lens, I can control, or I can set the microscope lens up according to how thick this cover slip is. And this range indicates how thick this cover slip can be. In this case, it can be between 0.19 millimeters, 190 microns, and 150 microns. Now, if you work with biology, you will know that these are marked as numbers for the cover slip. A number 0 cover slip will be this end, a number 2 will be this end, a number 1.5, like we discussed, will be 0.17, 170 microns. Because of that, I can have a correction color with which I can set this thickness. And this is important. If you don't set it up, like we discussed, the lens will work, but you will have spherical aberration. Much more than this also means that if you're working with a petri dish, the bottom of which is plastic and thick, you will not see through. Your image will be so blurred that you will not recognize. So if you're working with a petri dish, not with a cover slip on a microscope side, the bottom of the petri dish will become the cover slip. And that cover slip, the bottom of the dish can only be in this thickness range. So you cannot put a plastic bottom dish. So when you order your petri dishes, you have to make sure that it's covered with a proper glass with the thickness of, typically what I get from biologist colleagues is that 1.5, number 1.5, which is 170 micrometers. When you buy your cover slips, of course, the cheap ones will vary in thickness, which means that if you have cover slip thickness correction color on the lens, which not all of them have, because for example, this one we use the color for the immersion, but most lenses which only have one immersion, they do have a color ring that you can set according to thickness. you will have to play with that. Because you know, okay, I put the chief cover slit here between 160 and 180 micrometers. So then I play with this thing until the resolution is the highest. You observe something small in the microscope. On some microscopes, modern ones, this is motorized, so you can do this from the software. If not, you have to reach in and turn the color by hand, or which you need more hands. Perfect. Then let's see the various options. So this is what the lens actually looks like inside. And as you see, it's very far from having two lenses around. It has a lot of optical elements, and this is the front of the lens. This is where the lens meets with the sample, and then you have, for example, color correction units, spherical aberration correction units, and other devices which will then compensate for various aberrations. And this also means that if you damage your lens and it has to be repaired, then it can only be done in a special lens. So it has to go back to the manufacturer size, for example. And then what they do is they open this lens up in a clean room, so there is no dust in the air, and we have space suits. They replace the damaged glass, which usually it's the front element that gets damaged because people want to be a microscope stage. And or you use the wrong immersion liquid and it dissolves the glue that keeps this lens in place. This also means that you really have to be careful when you clean your lens to check what you can use to clean the lens. Because some cleaning agents that you get advertised by some companies will actually dissolve the glue, the cement that keeps the front lens in place. I also had this happen. And then you have to send it back. Typically, the cost of repairing a lens is half the cost of a new one. So the high quality lens that you saw in the previous slide cost you maybe 10,000 euros, so you pay 5,000 just to get it repaired. So you have to be very careful. And this is the tube lens that I told you about. So to make the light path here parallel, we have this extra lens, and this is something you can check by looking for this infinity signal. And there are a million lenses, blue ones, old ones. What you have, sorry, wrong button. You have to just match them to according to your demands, and we will talk about that now. Of how do we design our experiment in terms of how large is the object that I am measuring. And what I can do with the microscope is determined by the optical resolution. And I briefly mentioned that this is determined by the wavelength of the light and the numerical aperture of the lens. The wavelength, that's clear. Let's talk about the numerical aperture. The numerical aperture basically measures how much of the light that you illuminate the sample with will enter the lens itself. The more light enters, the more information you carry, the higher your resolution. The smaller objects you can see in the same microscope. The formula that describes the numerical aperture is simply the refractive index multiplied by the sine of the angle at which the light enters the lens, and this you understand better here. So this is the objective lens, it's an inverted microscope. This is your sample cover glass, this is the distance, which is the focal distance of the lens. You are focusing on your sample. Then the light that can enter the lens is determined by the size of the front lens and by the distance between the lens and the color aperture. And you remember when I mentioned a short while ago that the focal distance of the microscope lenses has to be short, because I want to keep this hole as wide as possible, so I gather as much light as possible. Optimally, this would be 180 degrees to collect all the light that comes from the sample. But this also means that if I move closer, I get a larger, and I get a larger sign, and I get a larger molecular temperature, I get a better resolution. So the shorter my focal distance, the better. On the other hand, I can also play with the liquid that I put between the lens and the colors. I can put nothing there, just leave air, which means that in simple geometrical optics, the diffractive index will determine what part of the beam that comes from the sample after, for example, fluorescence excitation enters the lens. Not much, because even if I'm fairly close, a lot of the light will go at a refractive angle that's above reaching the lens. But what if I put a drop of oil there? I suddenly get a lot more light into the lens. Now, why is that? It is because in order for the light not to enter the lens, after it entered the oil droplet, it would have to exit the oil droplet. But now we are going from oil, which is 1.5, refractive index, to air. What do I get there? I get total internal reflection. So a lot of light which hits the edge of the oil droplet at or above the critical angle will reflect. So the oil droplet works like an optical fiber. It leads the light into the lens. If I don't put oil there, the lens will work. But the numerical aperture will be much smaller because I lose all this light. I can also put water there. Water also does that, but the water only has refractive index 1.3. So much less light will suffer from total interval diffraction. So I lose quickly. But it still works. And I can put also glycerol, which is equal to 1.4. So this means that the focal distance and the refractive index of the material that I put there will determine the resolution of the microscope. So an immersion lens will give you better resolution than an air reflector, which does not use immersion. That's why these guys are also more expensive. It's also important that you put the proper liquid. So an oil lens is designed to work with oil, not with water, and vice versa. If you put oil on water of immersion lens, you will have a hell of a hard time cleaning it up because water immersion lenses can have a cement, a group, which is sensitive to, for example, alcohol or methanol that you try to use to clean up the water. You can do a lot of damage to your microscope. So in terms of numerical apertures, then this will be the order. The best one will be with oil, and then with water, and then with nothing. Why do we then even have air objectives? Why don't we always just put oil? But first of all, there's a practical reason. A lot of samples, they require that you scan a large part of the lens of the slide or the petri dish. And with oil, you just smear the oil around and eventually break the continuity. And that will go in your image. Water has the tendency of evaporating, of course. So if you have a live imaging experiment, water will evaporate. You let it up for overnight, and your image quality drops at midnight because the water is. For this, most modern microscopes have a water injection pump, which will add water throughout the experiment. There is also such a thing as water oil, which is a Zeiss invention, which is the refractive index of water, but the consistency of oil, which means that it doesn't evaporate so quickly. But it also means that when you are done with using, for example, an oil lens, you have to clean it. Because oil residue over, if let's say you do the experiment, it's going to take the whole away for summer holiday for 3 weeks, the oil will solidify and you regular agents will not remove it, so you have to send it to a specialist. Okay, so to calculate the resolution now we have the numerical aperture, and this is basically your most precise formula based on the Rayleigh criterion. We'll talk about that in a minute. But what I need you to remember is this: the rule of thumb, the wavelength of the light divided by twice the numerical aperture of the objective. This is only valid when you are doing fluorescence microscopy. When you are doing transmitted light microscopy, this is the formula. Because in transmitted light microscopy, the light will go through the objective lens and the ocular. In fluorescence microscopy, you will see the light only goes through the objective lens twice, once illuminating, once emitting. So then the two NAs will be the same, hence the 2 times NA. But for fluorescence microscopy, including confocal microscopy, this is the formula you need to do. So if you have green light, blue light at 500 nanometers, and you have a lens with an NA of 1, then the maximum that you can do is 250 nanometers. And if somebody says, okay, or your boss says, okay, I want you to measure these nanoparticles which are 100 nanometers, and I want you to count them. And this is the microscope you have, then you say, I cannot do that. Because my resolution is lower than the size of the object that I want to measure. But then if your boss said, okay, then measure mitochondria, which are 1 micron, and you say, okay, I need a microscope where I can see at least several pixels per filament, active, then you can judge, okay, can I do this or can I not? And you don't have to then go to the net and check the objective lens specifically. You can just use this rule of thumb. And then we will actually talk about very soon how to set up the pixel size to take advantage of the optical resolution. So there's a digital requirement and there is an analog requirement. This also means that the wavelength of the light has a tremendous effect on the resolution. So if you go from 400 to 800 nanometers, from light blue or deep blue to red, your resolution changes by a factor of 2. So this also means that when you set up your experiments, now you are much more smart and you say, my nuclei, which are big, should be measured with red because I don't need the resolution. And my actin filaments, or my Z01 signal, or cadmium signal, should be measured with blue. Unfortunately, the most typical nuclear signal comes from Jackie and Hook, which are blue. So oftentimes it's exactly the opposite. This is what it is. Or you just avoid measuring the nuclei. But this has to be kept in mind when you design your experiments. But realistically, whichever invisible lights, you're not going to get better than 200 nanometers. Okay. Why is that? It is because when light arrives at a very small obstacle, molecules, etc., it will not continue straight, but rather suffers what's called diffraction. That is a parallel beam that comes in and hits a very small object or a very small gap in a tissue. This very small object will behave as a source of spherical waves. It's like I flash my flashlight and somebody is standing on the top of that hill and he sees my flashlight. If you see Lord of the Rings, you know what I'm talking about. And then he will light up his flashlight or pile of wood. Nobody will know what I see. They will know that I signaled because he signaled. But the information of how long did I signal, did I signal a pattern, or did I just flash my light once? Nobody knows, because the effect was that he knew he has to signal. And then he flashes his light or lights the fire, and then people beyond that will see, and so on and so forth. So this means that if I hit a very small object, and now we know what size, 200, 250 nanometers, that size will work as a source of spherical light waves, which means I have the information that there is light coming from somewhere, but I don't know anymore what the source looks like. Because all the information that was carried here, intensity, shape, phase, is gone. All I know is that there is light. So this comes in, and then a randomish pattern comes out. What we see on the other side is then the interaction between these spherical waves. Some of them will enhance each other, some of them will cancel each other out. So I will have a so-called interference pattern. So this means that when I illuminate a very small object below the resolution of the microscope, instead of imaging a similar small object, what I will get is a pattern of interference. So this is called the airy pattern, and the center is the so-called airy disk. So what you will see is that you have a very small point source, and in your image you will have concentric circles. Bright in the center, then dark, then bright, then dark, then dark. It's an interference phenomenon. Depending on how far the interfering spectral waves are, like I said, they either enhance each other or cancel each other out. So what does this mean? This means that I still know more or less where the object is. It's at the center of this distribution of intensities. Do I know how big it is? Not really. The pattern itself depends on the size of the object in the wavelength. So I can guess what I don't know exactly. Plus, you will see it in the next slide that if I have two of these small objects close to each other, closer than the resolution, they will both generate an area pattern. But they are so close that what I see in the microscope is the merged area pattern. So I see again this baby biscuit shape. So I will not know anymore that this is two objects. I think that this is one object, one bigger. If there's only one such object, and it's smaller than the resolution, but by itself, I still know where it is exactly. But that means that I cannot have a second one next to it. But this is a principle behind one of the super resolution techniques, that I make sure that my molecules, which are smaller than the resolution, I only flash one molecule at a time in a certain radius. I never have two of them close to each other. So what determines how close these two guys can be, and I still see them as two? Well, the Rayleigh criterion says that if I draw the interference pattern and I look through the intensities, you will see in a figure in a minute, then the dip between the two peaks has to be 20%. Otherwise, the human eye cannot see it as two. So when you hear Rayleigh criterion, that simply means the dip between the two peaks is 20%. Now, what determines how close they can be? Well, one factor is how thin these peaks are. So how thick is the Rayleigh pattern itself? The area pattern, so the area pattern itself, and that's determined by the numerical average. And the other one is how close they are to each other. So if I want to increase my resolution, I can do two things. Or I can move my objects farther apart. That doesn't work. Or I can make, oh, that's my break indicator that we should have a break. Or I can make the thickness of the area pattern smaller. And this is the optical resolution. This is the numerical aperture. So if I have a lens with numerical aperture 2, then I have a big area pattern, 0.8, 1.3. This is why the numerical aperture matters so much. And that's the most important measure of the quality of the lens. Okay, let's have 10 minutes off, yeah, so you can relax, and we continue with that. Yeah, see you in. Okay, what continue? I mentioned that it's not only important to that's fine. We need some oxygen to the air conditioning doesn't work very well. That it's not enough to set up the microscope to the maximum resolution. It's also important that our digital system records it. Because if I have a very low resolution camera, for example, and I try to resolve high resolution microscope images, it's not going to work. So the question is, what should your pixel size be in order to be able to take advantage of the optical resolution? And the answer is quite clear. It should be twice as frequently sampled as the resolution. So this means that if your optical resolution is, let's say, 200 nanometers, then your pixel size optimally would be 100 nanometers. The reason for that is quite simple, is that if you have a periodic signal and you sample it at exactly the frequency of the signal, then there is a very good chance that you always either pick the peak, or you pick always halfway through, or always pick the bottom. So you will not see the pattern. You just see a flat signal like that. Now, if you sample the signal twice the frequency, then you will get sampling points near the peak and near the bottom, near the bottom, or here and here and here and here. So you will get the periodicity. You will not get the signal itself. For that, you would have to sample it much more frequently. But I don't want this. I just want to know the periodicity. For example, I want to know how far my bacteria are from each other, or how big my bacteria are. I don't need to have the details of the bacteria. I don't want to describe the exact shape of it. So this is the minimum requirement. You can also go higher. So most microscopes will give you an estimate. So when you look at the software size for micron, it will tell you optimal pixel size is so and so. This is based on such calculations. One thing you have to remember is that we don't go into the theory, but if you read about wave optics of spherical or curved objects, you will see that the optical resolution in the axial direction, the Z direction, is about 3 times worse than in the lateral direction. So if your microscope can do 200 nanometers or 300 nanometers resolution based on formula, then your Z resolution will be 3 times as big. So 3 times worse. So for example, from 200 lateral resolution, you have 600 nanometer axial resolution. So it's much worse. And there's nothing you can do about it. So this means that when you set up your images in 3D and you say, okay, I'm going to set my XY pixel size 100 nanometers, your Z step size can be 300. It doesn't have to be 100 because you are not getting any real information. You are just taking it longer and harming your sample. So basically what I illustrate here is that if your pixel size is as big as the optical resolution, then, like I said, you simply average out the signal. So even if there are 2 objects, you will see them as one, even if they, based on the Rayleigh criteria, they are separated. But my pixel size is too big and I don't see them. If I set my pixel size much smaller, then I have a lot of information which I don't need. I need to know where they are, how far they are. I don't need to have their exact shape, unless that's your target. So this is too low, this is too high, because it will then again harm the sample, takes much longer to collect so many pixels and so on and so forth. So the optimal is somewhere here. So you have enough pixels, so a small enough pixel size, so you are getting information about where these peaks are, so how far they are. So this is basically undersampling, this is oversampling, and these are optimal sampling. And this criterion is called the Nyquist criterion. You have to keep this in mind when you calculate or you set up your microscope. For this, you can either change the objective, or in confocal microscopes, you can use so-called digital zoom, which basically allows you to set any pixel size that you want. We will see in a few moments why. Now, the question is then, can we somehow characterize the effect of the microscope on the image formation itself? So, like we said, if the objects are small, then I don't see them as in their original and realistic shape and size, but rather I see a diffraction pattern. Well, I can, and this can be mathematically described with the so-called point-square function. The point-square function is basically a blurring function, a smoothing function, which will turn the object, which is basically a very small, let's say, a very small sphere, 100 nanometer sphere, into a diffracted pattern which looks like that. Why is it elongated? It's elongated because of what I said. The Z resolution is about 3 times worse than the better. So when I image a small spherical object below optical resolution, what I see in the microscope is a blurred cigar-shaped image. And that's not something you did wrong. This is the optics, the theory of optics behind it. Now, how do I go from this to that? Well, luckily, there is a mathematical step or function called convolution, which is basically, like I said, a smoothing function. You have the pattern, the smoothing pattern, and you move it through the image step by step, pixel by pixel, smoothing it, which will turn this object into that object. And what does this point-square function look like? Well, it must look something like that because it turns this object into that image. So it has to be a cigar-shaped element with that. But how do I measure that? Well, it's very simple. You put a fluorescent bead smaller than the resolution, for example, 100 nanometer bead. And you take a three-dimensional image of it. You will see in the confocal microscopy how this can be done. And then whatever this image looks like is basically what your point-square function looks like. Because I'm looking at the image of a very small object, and that's what the point-square function is. So it looks like that. This is a theoretical point-square function calculated by a software which takes into account the optical properties of a microscope. But I can also measure it. That's the green one. How do I measure it? Just like I said, I put little beads, 100 nanometer beads, into my sample. You can do it with an experiment, or you can do it separate from that, but it has to be the same cells, the same conditions, same laser. And then you measure it. Should I measure it? You should, because oftentimes the measured one is much bigger than the theoretical. So if I just use the theoretical one for what we will talk about next, I will underestimate the effect of the microscope. Problem is you cannot always measure. You are measuring the whole liver, and there's no way you can put little beads inside the liver cell. But if you measure them, these are measurements which we did years ago back in Berlin. These are beads inside bone marrow of the mouse. But you will also see that the point-square function changes depending on a lot of things. In this case, the depth of the tissue. The deeper we are in bone marrow, the more distortion we get. It's natural. There's a lot of scattering going on. The bone marrow is very dense. So this means that if I don't measure this, and I try to calculate what the image would look like without the microscope, so what would be the best image, I will underestimate the effect of the microscope if I don't measure them. But what if I measure them? Then I can inverse the smoothing function. The smoothing itself is called convolution, so the smoothing is called deconvolution. And if I apply the convolution on, this is the same bone marrow I showed you, After deconvolution, it looks like that. So this means that if I give this image to you and say, okay, please analyze the blue, green, and yellow signals and measure the size, distribution, etc., you will be puzzled by this image, but you can easily do this on this image because I resolved a lot more details after the deconvolution. So this is a crucial part of image analysis, which is typically the first thing that you do after you acquire your images. Now let's talk a little bit more about resolution and depending on the wavelength. In optical microscopy, you use visible light, for example, which is between 400 and 700 nanometers QoF. We have a large part of the electromagnetic spectrum that we don't use, and we won't talk about it. We will not talk about X-ray microscopy, electron microscopy. So we will only about this, and we also now remember that the resolution will depend on the light wavelength. So from blue to red, it gets worse and worse. Can I increase my resolution by changing the wavelength? Yes, you can go to UV. This will give you higher resolution. It will kill your cells as well and bleach your sample. So this is not really used. X-ray microscopy, of course, you get structure and chemical identification. Electron microscopy gives you the highest resolution, of course. This is now we are talking about nanometer range, so 100 times better than fluorescence microscopy. Special preparations are required. Slow. The field of view is much smaller, so it has disadvantages as well as advantages. The modern technique is combining fluorescence microscopy with electron microscopy. So you see both low resolution but well characterized fluorescence image plus the corresponding electron microscopy image. These are the wavelength range, so X-ray 10-fold increase, scanning electron microscopy 100-fold increase in resolution. Low resolution, 2-photon microscopy, which we will not talk about in detail, we don't have time, where you use infrared photons, so very deep red photons to excite fluorescent molecules. The penetration depth of infrared is much deeper than regular visible light, so you see through the tissue much more deeply. But your resolution drops by a factor of 2. Raman microscopy, it's labor-free. It provides you much lower resolution, micrometer range. So you will have Raman information about the chemical structure of your molecules, but from a much larger area than 1 pixel. So you will have a problem matching pixels with the Raman spectrum. And finally, a summary that where you would compare the various lenses that you have, magnification, numerical aperture, but most importantly, the resolution color. And based on this, you would see, for example, with the 100X, I have 220 nanometer resolution, so my pixel size would be 110 nanometers. And then you decide on which lens you want to use and which immersion liquid you need to use. And based on that, you can choose the lens that you want to use, and you can choose the immersion liquid based on practical and resolution concerns. Now let's see what real microscopes look like. And many of you work with them, so you know some of this already. We'll talk about the two configurations and the various light paths briefly. Microscopes can be built in upright mode, where the objective lens is above the sample. It has the advantage that it's easy to reach the objective lenses. So, for example, if you have to turn this correction cover I told you about to correct from the sample, the cover slip thickness, it's easy, but you have no access to the sample itself. So you cannot change solutions easily, for example. You have more than one lens, of course, in a turret, so you don't have to take the lens out and put it back on. Usually it has 6 spots, and then they can be no 4x, 10x, 20, 40, and 60, 100x, and then you have a full range of lenses with various immersion requirements. You can, in this case, for example, use a fluorescent light source like an arc lamp or a laser, illuminate through the microscope, and here you need a mirror because you want the light to go down through the objective lens and illuminate the sample. But then when you generate, let's say, fluorescence signal, that light will come back to the same objective lens. And then you need a special mirror here which reflected the excitation light, but does not reflect the emission light. And this will go to the camera or to the eye. This is then called a reflected or epifluorescence light path with an upright microscope. As you see, this has the advantage that down here nothing happens. So you can build the microscope in such a way that you only use one lens for both excitation and emission. And now you will remember the formula, lambda divided by 2 times NA for the resolution. That's why 2 times NA and not NA1 plus NA2, because I'm using the same lens twice. The big advantage is that if I use the other way, the second lens would have to have an equally high NA than the first lens. So down here in transmitted light mode, I would need a second lens as good as the first one. Otherwise, I will ruin my total resolution. So in reflected light mode, I can use one expensive lens and have the maximum resolution. In transmitted light mode, where I would illuminate the same way but pick up the signal here, I would need a second very big lens, or else give up some accuracy. Because of that, transmitted light images will have lower resolution than reflected light or fluorescence. I can turn this thing around. I get the lenses below. The advantage is I have full access to my sample. I can change the solution. I can set it up with an organ chip, with pump, blah, blah, blah. Because the top is free. Disadvantage, it's really hard to reach the lenses if you need to change the correction color, for example. But the most modern microscopes, if you go to TÜV, a philosophical way, they have motors to do this. So we do it from the software. The principle is the same. You illuminate the sample and then you either pick up the transmitted light or you pick up the fluorescent light. Now in transmitted light microscope, the most common application is get bright field or DIC or phase contrast. Either way you do it, what you have to keep in mind is that the microscope has to be set up, has to be aligned. If you don't do it, your resolution, transmitted light resolution, goes through the window. We don't go into main details, but many people do not do this or forget this or have the wrong information. So basically, the idea is that in transmitted light microscopy, the object is illuminated from one side and observed from the other side. So the light goes through this. That's the name. This is very useful when you have, for example, no labels, but you want to see the shape of the cell, nuclei, etc. Without labeling, then you take a transmitted light bright field image. However, this only works if the optical axis of this whole light path is set up very carefully. It's also important that the resolution is maximized, which is achieved by putting apertures in the light path to limit the width of the light beam that goes through the center. So this means that if I don't set up the optical axis and I don't align my apertures to match the center of the optical axis, I do get an image, but the difference in resolution is immense. If you ever played with such a system, you will know what I'm talking about. How to do it, I don't have time to explain, because it depends on the microscope. Every microscope will have a big poster behind it, hopefully, which explains you how to do illumination. The simplest alignment is the so-called Köhler illumination, which basically means focusing the microscope on the first and then the second aperture, making sure that the aperture is aligned with the light path, basically centering the light that goes through the aperture. You will know that you are looking through the aperture because you are looking at an octagon shaped light. We really don't have time to go through that, but what I get a lot from biologist colleagues is that, well, we are person in charge of the microscope, the lab told me that this only has to be done once a week, or whatever. This has to be done every time you change anything. Sample, the objective lens. Anything changed, you have to check the illumination. If you are doing transcript lighting. If you are doing only reflected light, fluorescence imaging doesn't matter because the light doesn't go through the transcript light. But otherwise, this has to be checked every time you change the dish or you change the objective. The main fields you will work with or main is simply bright field, phase contrast, and DIC imaging. Again, these days we don't have time for, we will go on this in the semester length courses. Here you simply take advantage of the fact that different parts of the tissue absorb different amounts of light. Bigger sample parts will be darker. In phase contrast, you take advantage of the effect of interference, where the light just outside the edge of the cell, for example, and just inside the cell will go through slightly different light paths. The light beam that goes through the cell goes through some fat light tissue, so this numerous different. Light that goes through right next to it does not have that, and then when you interfere that, you will see an interference pattern which will emphasize the edges. And that's what you get with a phase contrast microscope, an enhancement of the edges. With differential interference contrast, we take advantage of the fact, which we talked about before, that the polarization angle of the light determines the speed of the light. So this means that if I take a light beam and I cut it up into two different polarizations, perpendicular, then the two light beams will spread slightly different speed. And when I merge them together at the other side, I will get an interference. So I will get a DIC. You will see this in a minute. So in bright field microscopy, if the sample has light color, that's perfect. You put an RGB camera on the microscope and you have a beautiful image of plants, etc. We have projects like that. In phase contrast, like I said, we emphasize the edges, for which we need to have a special insert which looks like a donut. I think I have an image which shows it better, exactly. Complementary pattern. So below and above the sample, you have an annulus and you have a ring, and they have to be again aligned, otherwise you will not get proper images. But as a result of proper alignment, you will have the edges enhanced. And not only that, but because the light speed depends on the polarization angle, and the polarization angle depends on the thickness of the sample. It's a tiny difference. When you generate such a phase contrast image, the intensity in the phase contrast image is characteristic of the thickness of the sample. So basically, you can get for free depth information from phase contrast image. Most people don't do that, but it is definitely possible. So you can measure, for example, the thickness of the membrane of your cell with a very cheap method. Now in DIC, like I said, we artificially make two different polarizations. We don't rely on the edges of the cell providing us with different polarizations, but rather we use a special prism for the Wollaston prism, which will then give you a separate two beams. And then when they go through the sample, they spread at slightly different speeds. And when I merge them together with a similar prism, I will get an interference pattern. And what you get is these beautiful 2.5D images, with which you have a very typical shadow pattern around the samples. And when you, for example, train an AI model, they can recognize these patterns very, very easily. So if I have a DIC image of a sample which otherwise in bright field I cannot see the individual cells, and I do a DIC image of it, and then I train a model on it, it will have an easy time. So you need 10, 20, 30 images to train a model, and then you will have a very good segmentation. It has to be aligned. We don't have time to go for it, but basically it involves setting up the Wollaston prisms on both sides, so that the 3D effect, so to speak, is maximum. If you don't set it up properly, you just get a flat 2D bright field image. These systems are more complex. It needs a polarizer unless you use a laser, in which case it's a polarized light already. You need two of these prisms. One of them is sitting right below the objective lens. So you can always tell, like, here's my microscope set up for that. If you look at the objective lens and directly underneath it, you will see this little thing sticking out from the lens. And then you use this screw to move the prism to maximize the 3D effect. And then you get images like that, where you can really, it's a really flat sample, like a micro more or less. So now I see fibers, I see various compartments. This is a fibroblast. By a very cheap technique, with such a film costs you like nothing. Okay. But most of the time you will be dealing with fluorescence microscopy. So let's talk a little bit more about that. First of all, we need to talk about what fluorescence is and how we can use it for microscopy, and then how to design the experiments in terms of fluorescence. So when this holds true also for confocal microscopy, it is just a method of fluorescence microscopy. So like I said, we will limit ourselves to the visible light range, and we talk about mostly the light as rays and waves. So what happens when I illuminate a molecule with a laser light? Well, as you know from quantum mechanics, the molecules can absorb energy only at certain times. We have various energy levels. We have the base level where the electrons are at the lowest energy possible. This is what they like to be. But these electrons can also absorb energy if you, for example, illuminate them with a laser, which will make the electrons go to a higher energy level. But they don't like it, so they come back. How fast determines whether you are dealing with fluorescence or phosphorescence. But what happens is that the excited electron, which doesn't like to be here, tries to lose some of its energy that absorbed from the light. This could, for example, result in a vibration of the molecule. But ultimately, it will get to the bottom of the excitation level, and the only way to relax back to the ground energy level is to jump. And when it jumps, it needs to emit a lot of energy, because the energy has to be resolved saved somewhere. So the energy that was stored by the electron has to go somewhere before it can go down. Where does it go? Well, in fluorescence molecules, it will be emitted as a photon. So the visible photon gets absorbed, the electron relaxes a bit, and then jumps back and releases another photon. Well, it lost some energy here. So the energy of the photon that comes out is less than the energy that came in. Now, if you remember basic physics, the higher the energy, the higher the frequency, and the lower the wavelength. So blue light has more energy than red light. So if I illuminate this sample with blue light, I will get green light. If I illuminate with green light, I will get red light. So that's very lucky, because this is called the Stokes shift. This is very lucky because if the two wavelengths were the same, with the microscope they would get mixed, and I would not be able to separate illumination from excitation, from emission. And we talk about this later. But they are different. If you have a complex molecule, then of course these energy levels are much more detailed, but the principle is the same. You go from base level to excited level, relax a bit, jump back. But since we have sublevels, the electron can go from here to here, or from here to here, or from here to here, and so on and so forth. So there is not only one energy that this system can absorb, but a range of energies. So there is a spectrum, an excitation spectrum, which tells me from which level to which level does the electron go. So this means that if I say GFP requires 488 nanometer excitation, that's not true. 488 nanometer is the wavelength at which it has the highest probability to absorb a photon. But it will absorb 482, 478, 492, and so on. But with less probability. So this means that I can plot the probability at which the molecule will absorb a photon. That's my excitation spectrum. But this also means that when the electron jumps back, it can come from a lot of sublevels in level 1 to a lot of sublevels in level 2. So the emitted photons will not be one wavelength, it will be a range of wavelengths. So there is also an emission spectrum. So for any fluorescence experiment, you need to know what is my absorbance or excitation spectrum of the molecule, and what is my emission spectrum of the molecule. So for example, with Figge, which is very typical of Alexa Flow 488, these are the spectra that you will get from the website of the provider of the molecule. Now, why do we need to know? We need to know that, first of all, to design the microscope in terms of which laser or light source I should use. I fix it, then I have to have a 488-ish light source, whatever it is. And I need to have a filter, we will talk about in a minute, which lets me detect the emitted light by Figge or Alexa 488, which is like 510 or so nanometers plus minus 10. If I don't know this, then I may not see anything because I said the filters are wrong. The other reason I need to know this is that what if I want to use more than one layer? I mean, it's very difficult to imagine a biology experiment in one color. We have, let's say, 3 or 4 colors. And I want to see these objects inside myself, for example, separately. So I have to label them with different colors. But if the colors are too close, then they're going to overlap. And if I use a yellow and an orange label, then I will not be able to tell is this object 1 or object 2. So I need to know the spectrum. Now, we have to separate the lights. And as I said, excitation and emission wavelengths are very luckily different because of the Stokes shift. So I can build a device called the dichroic tube, which is the heart of the microscope. The wheels were the objective lenses. Without this, it will not work in fluorescence. But basically, this little device does it look just like that. It has a filter for the excitation light to choose the wavelength that you determine based on your excitation. Let's say 490 nanometers. These filters are usually bench pass filters, which means they let through a certain range of light. Let's say 470 to 490. It has a mirror, the so-called dichroic mirror, and it has another filter for the emission. The size, the range of this, again, is determined by the emission spectrum. Now, what about this mirror? This is a special device set up at 45-degree angle, which reflects above, which reflects below a certain wavelength, but it's transparent above a certain. So, for example, with Alexa 488, I will set this up so that it reflects below 490 and lets through the light above 500, so 495. What this means is that if I illuminate with a 488 laser, it will be reflected. It will go to the specimen, to the objective lens. But then, because of the Stokes shift, my emitted light will be 500, 510, etc. So now this will go through. And then goes through the emission filter and through the camera for the detector. So without this, we could not separate the two wavelengths. And without the Stokes shift, there would be no filter. And this is what these guys look like. Usually you have 3 or 4 of these or 5 in the microscope, so you don't have to open the microscope and change the cube. So when you have the TAPI, Alexa 488, Alexa 561, Alexa 7, whatever, you put the proper dichroic tube in the light path, then you're working with these different dies. The two different configurations have, of course, different locations, but they are usually like an openable door behind which lives a turret, and in that you put these little things. So when you do your experiments, you go to a microscope, you need to know what wavelengths they are used for, what kind of dichroic tubes they have in the microscope. And if you have a new dye, which is like a unique wavelength, like let's say, it's not unique, but for example, YFP 514 nanometers, then you must use that label. A lot of microscopes will not have a 514 tube, then you have to buy it. You go to microscopes, okay, my group is able to spend 150 euros, you buy your cube, then you put this in the microscope. Some cubes will work outside their range, but the signal will be, of course, then very weak. So what do we need? We need the excitation spectrum, and we need the light source. Well, in the old days, we used to use mercury lamps for that. And that's a problem because this lamp doesn't have a continuous spectrum, excitation spectrum. So for example, if I wanted to use this with Fitzy, it wouldn't work because exactly there is no light. But usually we use diodes and lasers. With a diode, you have a range of wavelengths coming out, and with the laser, you have a 1 to 2 nanometer wide, very narrow excitation. So when I say 488 nanometer laser, I mean plus minus 0.3, 0.4, very, very specific. So in this case, if you use a laser, you design it to be close to the peak of the excitation spectrum, as close as possible. Diodes, they give you a range. So they give you like a peak-shaped excitation spectrum, which you try to match. Diodes are much cheaper, of course, but they also carry less power. So for confocal microscopy, we usually still go with lasers. And for regular fluorescence microscopy, you can use diodes. And then you need to know the emission spectrum, both to set up your detector and to separate your various colors. If you only had one label, then you can say my detector should pick up everything from around the peak of the emission spectrum. Then you get all the photons, and you get a bright image, and you're very happy. The problem is that if you have a second label, then you will also pick this up. So you will then need to use a bandpass filter, which is specific for that dye. And then if I have more than one label, then I have to have a match where I know both the excitation and emission spectrum for both. So for example, CFP, YFP, I know that this is my excitation, this is my emission, but I will also see that my emission spectrum from this might overlap with the excitation of the YFP. So now we start the example. We have multiple colors, and the spectra are not very thick. So the excitation and emission spectra start to overlap. We have a crosstalk. What can I do about it? Well, I can design my filters as precisely as possible, as narrow as possible, to avoid this overlap. But then the narrower the filter, the fewer photons I get, so the darker the image. With very bright sample, that's fine. With not so bright one, that's a problem. And even with two labels, now it starts to look disturbingly complicated. And if you have 3 or 4, which you often do, then this gets really. Two solutions: control samples, where I illuminate every label with every wavelength, even if it's not matching wavelength, and measure how much signal do I get. Let's say I illuminate GFP, which means 488, with my 450 nanometer blue laser. Shouldn't get any signal, but I do. Let's say 10% as much as the real image. But now I know how to compensate. And I do this for all pairs. Or I scan one by one, image by image. I illuminate 48, take the 48 image, I illuminate 504 or 5 for that image, and so on and so forth. Disadvantage, it takes as many times as long as the number of columns. Most often, unfortunately, it cannot work going this way. So parallel scanning, which would be the first choice, is very rare because the overlap between spectra is just inhibitory. So practically, this is what you will, in most cases, do. So it's just an example with only two different labels. These are the images that you must have. You have to have an autofluorescence image because you never know. Some samples are really bright already, and you must compensate for that. Then you get the various combinations of primaries and secondaries, and the various wavelengths. Which means that if you don't do this, and then you acquire a whole bunch of images, then you have you are locked down because you cannot analyze the images. Because you don't know how much crosstalk you have. In terms of mounting medium, anti-fading agents to protect the label, this we will talk about in a minute. That has an incredibly wide emission spectrum, so I hate them. Because they bleed into everything. The good thing is the shape of the nucleus is very recognized. So if I have a crosstalk measurement like I mentioned, I can determine the shape of the nucleus very easily when it's last minute. I can compensate for that, and this we do often. So it's not a big problem, but we don't like it. The bottom one I want to talk about.
Instead of ducking, we will just not to stay in the nucleus.
Yes. But sometimes you have to, so I understand that. I live with it. we don't sleep over it, but we don't. So because sometimes people come about and say, exactly, I'm like, what about the nucleus? Oh, we don't need that. So we don't measure it because I get glue everywhere and so I don't want that. You know, so if you need it, measure it. There are red labels, but I know biologists don't like it. I don't know the biologists, so I don't know why, and I accept it. But it's not possible. But if you don't need the nucleus, then please don't use it. Or take a transmitted light image and I'll get nucleus from there. If you only need to know where it is and how to get it, or how many, I can do this from there. And we will learn it. So you don't necessarily always have to label it. I wanted to talk a little bit about this one. I don't have a slide, unfortunately, but you will understand me. Should I use oil objective? Should I use water objective? Should I use laser objective? Well, it depends on the light path. How deep you have to focus into the sample to get the area that you want to find. Just imagine you have a tissue or a multi-layer of cells. You have to focus 50 micrometers into the cell. So it's far from the colors. What will the light do? The light will come from the objective lens, goes to the immersion medium, goes to the cover slip or the bottom of the petri dish, goes to whatever is the sampling, usually water or water light, and then gets to tissue, gets to the cells. So it travels from glass to something to glass to water. What do I do here? I put water. Why? Because I travel a lot in water inside the sample. If I put oil, the deeper I focus into the water, the more the aberrations. So the signal will get gradually worse as I focus deeper and deeper, because now I go through a certain amount of oil, which of course helped that in the beginning. When I go from lens to oil to glass cover slip, that's the same refractive index. There is no error there. But then I go into a very different refractive water. So this means that if I now focus deep into the tissue, the deeper I am, the worse I get. And I somehow have to compensate for that. So I have a point thread function that looks like that. It widens very, very quickly as I focus deeper. But if I put water, then yes, I will add some error when I go from the objective lens to water to the cover. But this is a constant error. I can compensate for it. And then I go into water. So now as I focus through the sample, let's say it's a 100 micron thick cover slip or organizer. Throughout these 100 micrometers, I'm always in water. The same material that I have between the lens and the microscope. So yes, I have a bit more error because of the mismatch at the beginning, but this error is constant throughout. So my image will be homogeneous. A little bit worse, but more. The other way, it will get much worse as I focus. So if you have a choice, keep this in mind. On the other, if the sample is stuck to the cover slip, it's a monolayer of cells. I go from glass to something to glass to the tissue right away, and I put oil there. Because I'm not traveling in the sample more than a few microns. But then, if I put oil here, there is no error introduced. The light doesn't even know it's in a different medium. So the sample is close to the cover slip, oil immersion, typically. The sample is thick, and I focus deep, match the refractive index of the sample. Okay. So, summary. Now we know we talked about all of these things. How do I get images where I actually see the three-dimensional structure of this sample? If I use a regular fluorescence microscope and I look at a monolayer of tissue, I get beautiful images. I don't need anything more than that. But if I look at multiple layers of cells or a big tissue, I look through it in fluorescence or transmitted light, what I see is a blur. Why is that? It's because when I excite such a thick tissue, I get signal from everywhere. And even though I focus on a certain focal plane, nothing is keeping the light out of focus to get into my camera. So I get a blurry image. So what do? Well, what people used to do was take the tissue and slice it up. You still do that sometimes. With a microtron, you cut it up into micrometer, a few micrometer thin slices, float them on water, put them on cover slip, image them. This still works. It works well. The problem is you can then eat the slices, and the tissue is gone, so it's not a liver there. You want to slice. People still do, and we get images, and they're perfectly fine. But can I do this optically? Can I do optical slice? Yes, we can, and this is called focal microscopy. And here's the principle. It's very, very simple. If I have a sample, a thick sample, and I focus on a certain part of it, I will get signal excitation reduced, excitation induced emission from everywhere in the sample, mostly from the focal plane, yes, but from everywhere else as well. So I will get these blue, magenta, and green beams of light, blah, 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 to my detector. So I get a blurry image. But what happens if I put a piece of metal here and punch a teeny hole in the middle? What happens is that, of course, only the light which fits into this hole will go to the camera or the detector. Now, if I'm smart and I set up the position of this to match the focal point of this lens, then whatever is in focus here, in this case the magenta, will be the light that gets through the hole. The green and the blue will not. So what did I do? What I did was I limited my detector to see a thin layer of my sample by blocking out the rest of this. Disadvantage, I lost a lot of light. All the light that came not through the hole part. Those photons hit the metal plate of the car. But I get a sharp image in the sense that I'm only getting an image from, let's say, 1 micrometer away. What did I do? I sliced the sample optically. The position of this object, so this object is called a pinhole, because obvious reason, has to match the focal point of the system. So the focal point here and there must match. So the system is confident. The two focal points match. If this is positioned wrongly, then what you get in the detector is not what you are looking at. So it's a misaligned from focal. In older systems, you can do this yourself. In new ones, it's fully automated. So this is perfect, but it's not, because I lose a lot of light. But I can do that if I have a very good detector. Secondly, I'm only getting light from a very thin layer and from a very small spot, wherever the laser is here. Okay. And I cannot use an arc lamp because I don't have enough intensity. I use a lot of photons here. So I need a strong light source, and that has to be a laser. So, but lasers are very small spots, maybe a micron after focusing. So I get signal from 1 cubic microns, 1 by 1 by 1 approximately. I don't see my whole sample. So what I have to do is I have to scan the sample. I have to move the laser beam both in the X, Y, and the Z direction. Well, that's the price we have to pay. So this is laser scanning confocal microscopy. So basically what you have is move the laser in the XY direction, very quickly in the X and more slowly in the Y until you have this pattern that you scan the entire surface. And then you change the focal plane, scan it again, change the focal plane. How much should we change the focal plane? It's based on the optical resolution mixed with the Memphis criteria. Remember, if it was 100 nanometer pixel size in XY, then it's 300 nanometers in Z. So I move my sample or my objective lens in 300 nanometer steps to the Z. And I set my pixel size, and we'll talk about this, to 100 nanometers. So what happens? Laser, we still need the diode as usual, because it's just a fluorescence microscope. But this is then the main part here. We can also put a pinhole here, but you don't have to. And then you have to scan in XY and you have to scan in Z. How do I set the size of this pinhole? If it's big, it's like if it were there. If it's very small, it gets thinner and thinner. The layer from which I get the signal gets thinner and thinner, but I guess I get less and less light. What is the optimal setting? Well, the rule of thumb is we set it to 1 area unit. Now, what the heck is an area unit? You remember the area pattern, the very small object which generated this concentric circles. The size of the first maximum, which was the inside first peak, is called 1 area unit. And this is important because if you detect just that spot and you ignore the secondary and tertiary maximum, you still get like 83 or 87 percent of the energy that was. So you get almost all of it. So the unit that they use for this one instead of actual millimeters is area units, which means that the pinhole size, the ultimate pinhole size depends on the point spectrum. But that's natural. You have to match the point spectrum. So this means that if the diameter of the first area maximum is 200 nanometers, which means our optical resolution is 200 nanometers, then I can set this pinhole to what would be 200 nanometers before magnification. But let's say we have 1000x magnification, let's say 100x objective lens and 10x ocular lens, or 10x lens before the camera or the detector. And this would have to be 200 nanometers times 1000. And that would be the actual size of the pinhole, so the size of the whole microscope. But if I tell you that my pinhole size was, I don't know, 10 micrometers, that doesn't tell me anything. But if I tell you it's 1 area unit, I know that under those conditions, whatever the color was, whatever the lens was, it was matching the first area maximum. That's much more informative than the physical size. If I open the pinhole, what happens? Well, I get a much thicker layer, and it ceases to be a confocal microscope. It turns into a wide field fluorescence. This has the advantage, of course, that you don't need two microscopes. If you have a confocal and you don't want to buy another fluorescence microscope, let's open your pinhole. Of course, that's a very expensive way to have a fluorescence microscope. You can have for 15,000 euros a fluorescence microscope. So, optimal as a rule of thumb, we send the pinhole size to 1 mm. But if I open a pinhole, I get less confocality. Should I close the pinhole? And these curves show you what you should do. This is the axial resolution. Full bit, half max, doesn't matter. The smaller the number, the better the resolution. What you see is that this is in area units. At 1 area unit, this is where the curve is. And then if I open the pinhole, my resolution gets worse and worse, of course. But you also see that if I go down to like 0.6, 0.7 area units, after that, nothing really happens to the resolution. So if somebody says, oh, I'm so smart, I set the pinhole unit to 2.0.2, because that's the minimum in microscope amount. What did you do? You moved from here to there. So you gain nothing in terms of confocality, but you lost 8% of your focus. So whilst microscopes do allow you to do that, it doesn't give you anything much. So I would say beyond 0.5, 0.6, I would not go. Between 1 and 0.5, there's still something. So that's still worth exploring. Now, what happens to the lateral effect? Some people say optical microscopes are super resolution microscopes. They are not. The maximum you gain by closing your pinhole down is maybe 20, 25% resolution. And the price you pay is you lose a lot of light. So confocal microscopes will help you with optical slicing in the axial direction, but not so much with the lateral resolution. Typically, we say 20% gain in the lateral resolution. And these are just some comparison photos. So if I give you this with an open pinhole, you will be puzzled what I want from you. If I give you this, you have an easy task of counting how many objects. Of course, that also means that you have to, this is the comparison between 1 and 0.5. If you draw a line, you still see an increase of like 20%, but not much. So you have to be clever about that. Further examples. Just a little bit of theory. So confocal microscopes existed since the mid-50s. That's the first time when Minsky thought about this, and he built his prototype at the MIT, Massachusetts Institute of Technology, which looked like that. And he already discovered the principle that you need a pinhole to do optical slicing. And Minsky loved to invent things and then never did anything with them. So he built his first confocal microscope. He used an arc lamp with a mirror as light source. You can use anything. That's not enough light usually. And then he set it up on the corridor and forgot about it. And the other reason we know about this the prototype rebuilt in 1885 was that his son-in-law was a lawyer, and he said, "Oh, we should patent this and get some money for it." And we patented it, and I don't think we got money for it, but that's why we know that he invented this. And the first commercial one didn't exist until I would say 97. And the reason was that the principle is very simple, but the practical difficulties are tremendous. For example, you have to scan the sample because you're eliminating this problem. How do you do that? What Minsky did was he moved the sample through the table, the microscope table, and put it in a motor. It works, but you can imagine this is very sensitive to any noise. Anybody walks by, the whole thing was just full. So you had to come up with an idea to move the beam instead of moving the sample. So for example, what after some steps, what they came up with was to have mirrors that oscillate. And then there's one mirror which will move the beam in the x direction, and this has to move very quickly. So we go from left to right in the sample, for example. And then I put a second mirror, sorry, the other way around, x, y. And then I have a slower mirror which, once I scan from left to right, I move the beam a little bit down. How much the optical resolution by the Lindquist, so 100 nanometers, for example. And I scan again, left to right. And I move it down by 100 nanometers properly until I cover the whole sample. Now, when you look at your confocal image, it says 1024 by 1024. What does that mean? That means that it moved the beam 1024 times along the y-axis. What does the other 1024 means? How many little dots in the image will it detect? You will get from that, right? One. The beam is moving continuously. So what does this 1024 mean? The laser doesn't go like that. It just goes continuously. So what is a pixel then in a confocal microscope? Right? The pixel is up to us. A pixel is how long I decide to sample the emitted photons. If I say I sample for 2 microseconds, and the scan from left to right takes 2 milliseconds, then I generated how many? I generated 1,000 pixels. Because I said 2 microseconds versus 2 milliseconds. If I say 10 microseconds, I generated 5 times fewer pixels. But since I collected light 5 times longer during the scan, I get 5 times as many photons. So the number of pixels that you set on your microscope determines how long you collect the emitted photons during the scan from left to right. The longer you collect, the fewer the number of pixels, but the brighter the image. So there's a limit. You cannot have the pixel, which you this way determine, so you shouldn't, be then smaller than what would be determined by the Lindquist criteria. So if I say my lateral resolution is 100 nanometers, then what the beam moves when it's moving left to right during the collection time should not be more than 100 nanometers. Actually, it should be 100 nanometers. I know the scan speed. I mean, you have to know this, but the computer software, the microscope software knows. If you say, I want my pixel to be 100 nanometers, then what it does is it checks the scan speed, how fast you set up the mirror, which is moving from left to right. And says, okay, it's moving from left to right in 2 milliseconds. And this guy told me he wants to be the pixel size 100 nanometers. And he told me to scan 500 micrometers or 100 micrometers sample size. Now I can calculate how long I have to collect light for 1 pixel. And then when you look at the software, the science software, it says optimal pixel time. That's how it calculates. It says, because you say I want 1,000 pixels, or 1.4 pixels, and it says, okay, then your optimal pixel time, or before it dwell time, so how long the laser would dwell at this certain moment, should be 1.2 microseconds. 1.2 microseconds is actually usually what size we record based on the. So pixel, yeah, laser scanning confocal microscope is completely virtual. It's up to you how big, how fast the pixel is collected for and how big the pixel is. So it's not like the camera-based fluorescence microscope. The camera chip contains a certain number of CCD chips, and the size of which is whatever, 6 microns, and then your pixel size is what it is. It's determined by the camera, and it's determined by the objective as well. confocal scanning, laser scanning confocal, it's entirely up to you. So you can set up your optimal experiments according to the Nipis criteria, very well and all of these details about the electronics, how long it takes to go left to right, blah, blah, blah. This is set up by the software. Within all days, you have to set it up yourself. And then you get this complete setup. It's otherwise just a fluorescence microscope with the added advantage of being able to control your resolution. Now, since we lose a lot of light, we cannot really use the camera. The second reason for that, namely that the beam moves. Because as I scan the sample, the light beam that hits the sample moves left to right and in the line. But this also means that the emitted light could also move. But we cannot have that. We cannot have the emitted light move across. So what we do is so-called descanning. If I go back here for a second, it's called descanning, which simply means that the emitted photons are also going through the same scanning mirrors that the emission, that the excitation photons do. This means that whatever movement the mirror forced on the excitation will be forced inwards on the emitted, which will mean that the emitted light will not move. It's good because otherwise you have to chase it. But because of that, I can switch from a camera to a so-called photomultiplier, which is a much more sensitive device. And it looks like that. So the principle is that you let a photon enter this vacuum tube where it hits a metal shaped accordingly. And this is from a group of metals where the electron at the most easily excitable level is so easily excited that having a visible light photon hitting the metal will kick out one electron from the metal. And then you have an electron hanging out here, not doing what to do. So what you do is you put a second electrode here, and you put a large positive voltage in there. They got these electrons like that, so they will accelerate toward their new home here, and as they accelerate, they gain kinetic energy. So now they have more energy than they had before. So when they hit this metal, they will knock out, let's say, 2 electrons. And then you put positive voltage here, so now they are happy and they come back here. And now they knock out 4, and then 8, and then 16, and so on and so forth. So what you're doing is, it's my 10-minute warning. So what you are doing is, you are multiplying the photons. From one photon, you get 1,000 electrons. How many? This depends on the voltage that you put here. So when you go to the size control, when it says gain 700, that's not a random number. There's 700 volts between these two so-called diodes. The higher the voltage, the more the electrons accelerate, the more electrons they knock out, so the higher the gain. But above a certain level, you saturate the system. You cannot knock out more electrons. So if you turn the gain on the confocal microscope to 1,000, switching 1,000 volts here, you knock out so many electrons that there are no more. So when you go from 1,000 to 1,200 gain, there are no more electrons. So you think that you get more signal, but you don't. You are physically saturated your system. So now you don't see the difference again. And then from the detector, you just get a continuous current coming out as the electrons arrive at the detector part. And we sample, so this is what the sample actually looks like. If you ever look at an oscilloscope, that's what it looks like. These are photons hitting the multiplier and then generating current. And then this is what a pixel is. I say, let's collect this direct current from the detector, from the photomultiplier, for 2 microseconds. as I get more and more electrons, my integrated signal goes up, and the area under this curve is my fluorescence intensity in a computer microscope. So this pixel is less bright than this one, but this pixel is much brighter than that one. And this interval for how long I integrate is the so-called dwell time, which determines how large the pixel is. If I say cut the pixel size in half, that means it will collect for half as long, then I will get this much signal here, this much signal there. So now I have two pixels, I will see the difference. This pixel will be brighter than that one. But at this current setting, this will be one pixel and it will be this bright. It's all up to you to set this up. Light sources, typically lasers. You can have diodes, they don't usually have enough energy to compensate for the problem. In the old days, arc lamps were used, they were dangerous, and they had a very uneven spectrum, so you really have to match your filter according not only to the dye, but also the spectrum of the arc lamp. So we don't do that anymore. The point at the pinhole, like I said, you only get signal from maybe a micrometer thick layer, depending on the pinhole size. So you have to have a lens to scan through the sample in the Z direction as well. And then this also means that the three-dimensional image that you see is the result of calculation by your computer. You don't see it per se as a real image. Also, there is no image in a confocal microscope. It's just current and integrated current, so you have to calculate the image. So you don't see anything without a computer. Resolution, there are formulas which you by no means should remember, with which you can calculate the axial and the lateral resolution. And this is the little difference, the 20% difference that, as I mentioned, in lateral resolution between a fluorescence, a wide field microscope, and the fluorescence control. So keep this in mind, but don't counter it. This is the main that you run it for. And this is the axial resolution. Again, you don't use this formula directly, but when you use the software on the microscope, they will tell you, like, under these settings, what is your so-called optimal step size? And that's based on this formula which they calculate. So you don't have to do that, and it depends, of course, on the pinhole size in chance. Now, in order to really take advantage of the resolution, though, it's still important that you have enough photons. If you don't have enough photons, this is what happens. This is a pattern where the microscope was set up optimally, but if you set up the pixel size or the dwell time so short that you only get 10, 50, 100 photons, what you see is the real pattern is not revealed. So even though I have everything set up properly, I did not collect long enough, so I only have so few photons that the pattern is not revealed, which means I lost my resolution. And this is the rule of thumb I would like to remember. You need approximately 500 photons per pixel before you can reliably take advantage of the resolution, the optical resolution based on the image. And if you take any of these classes where optics goes deeper, this will be things that you hear that you need more photons. You need more photons. Detectors, we have talked about that. I would like to very briefly talk about how to set them up. Let's say you look at your confocal microscope and you see this image. You see that the background is brighter than they necessarily have to be. You also see that your top signal is not saturated in the photomultiplier. We talked about that. This is fine. You can image that, and then you can get rid of the background in image analysis and get the segmentation properly done. But this is not optimal. One thing you can do is that if you are sure that this is background, you can lift this level down to 0. Why can I do that? I can do it because I'm detecting the photomultiplier. It detects current. I can shift that down as much as I want. I can shift this down so much that it goes to negative and this is careful. But there is a background offset button on the confocal microscope which applies to the PMT, the photomultiplier, and subtracts a certain current. And now you have this signal. But then you realize that this is silly because the saturation level of my PMT is here. Why am I only detecting 20%? I can analyze this, yes, but I can analyze it even better if I increase the gain on the PMT. Let's say this was at 400 volts, this is at 600 volts. You get the point. Now I get a nearly black background, and I get a not saturated but fully filled up dynamic rate of my PM2. And this I get this into. And this will require much less pre-processing than this one. And pre-processing alone is risky because you are removing something that you should not. So the best you can do on the analog side, you can. Don't over it. If you compensate too much, you might get rid of the dim signal like here, and then you made a big mistake. So if you're not sure, leave it alone. So only do this if you know what you're doing. This is just a table where I compare that indeed wide field microscopes perform much more poorly than confocal in terms of resolution, and also that lateral resolution doesn't improve as much. But this is just a little summary. And then finally, I wanted to talk to you briefly about an improvement of confocal microscopy, which you will see if you work with them. We have several of them, and that's the area scan method introduced by Zeiss. And this is almost like an on-chip deconvolution method, which does increase the resolution by 1.7. Lateral resolution. And this is how it works. The problem with confocal microscopy is that I have a pinhole, and that cuts out a lot of the light. Without the pinhole, there is no confocal microscope. So the clever idea was, let's replace the pinhole with a honeycomb structure of very tiny photomultiplier tubes, 32 of them. That's made by Hamamatsu. The size of one pinhole would be, one air unit would be about this big. So if you choose the middle 7 micro detectors, that covers an area approximately 1 air unit. But what you do is the following. You put this where the pinhole would be. Because the point of the pinhole is I need to know which photons come from this very thin layer into the nucleus. But I can also tell this from here because those are the photons which hit here. And the photons which are out of focus, or coming from out of focus, will hit here. So it works the same as a pinhole, but it doesn't lose light. But what it does is it detects the signal from all of these. I think this one is not detected. Only 31 is actually measured, or whatever it is. What I get is similar to the signal that I showed you, the PMT analog signal, for 31 of them. And each one will belong to one of these honeycomb tiny detectors. So if I integrate the signal for these 7, oh yeah, by the way, I forgot to say, this size is 0.2 air units, one of these. So if I collect these 3, that's 0.6 air units. Yeah? So I get the signal integrating those 7 as if I had the pinhole, real pinhole at 0.6 air units. If I plot this signal alone, that's 0.2 air units. If I put these 5, that's 1 air unit. And the total is 1.25. Now, if I go back, I should have the second copy. If I go back to, sorry about that, here, what I did was, and this doesn't cost me time because I do the measurements parallel to multiple AD converters. I measured this curve here, here, and here, and here, and here. I measured this part with one measurement. So what I can do is I can fit the curve and I can extrapolate what would the image look like with zero pinhole. Zero pinhole is the optimal setting. This is when the confocal microscopes behave the best. But I cannot close the pinhole to zero because there is no focus. But with an area scan, I can extrapolate because I can measure several points on this. So what I did was I calculated what the image would look like had the confocal pinhole would be close to zero. And this gives you, like I said, approximately 1.7 times better resolution, and it also can increase the scan speed. So you will switch to this unit if you need to improve your resolution or you need to scan it faster. There are, of course, many other modalities for microscopy. Spinning this confocal microscopy where you use multiple pinholes, and you don't have so much control on the pixel size, super resolution techniques. But for these, we don't have time because of the 3-hour limit. But in your practical life and images that you deal with will be from mostly from fluorescence and confocal microscopy. I thought this would be very important to understand how these systems work. And then based on that, you can also extrapolate your knowledge and read up on how various modalities work. Yes, we have a course in every October for those of you who are at the university at lower graduation level that you can take, where we teach microscopy, image analysis, and modeling in the whole semester. If you're interested in more, you can also attend that. I think we are pretty much on time. So we will stop here, and if you have questions, you can ask them now or later. And before I go to you, those of you who need a laptop, please stay behind. I will take you upstairs to Ahmed and give you the laptops. Yes.
Yeah, thank you very much. So I just want to clarify something. So we look on focal microscope, and you were highlighting
Yes.
and also that's what would be also in relation to super resolution microscopes like STED microscope.
Yes.
What would be the dynamics using this pinhole since the STED microscope uses the students aperture into it? What where the range be on this graph?
Yes. So the question here was about super resolution microscopy, especially STED microscopy. With STED microscopy, those of you who learned about it, you replace the solid spot, so to speak, with which you illuminate with a donut, which is a combination of two lasers. And the idea is that you have a high energy laser which illuminates in the shape of a ring. And then you use your regular fluorescence laser focused in the center of this ring. So it looks like a donut in the middle of which there is sitting a little button. And the advantage of that is that the high resolution with a high power laser which illuminates the donut basically puts all those molecules out of excitable state. So they will not illuminate at the same range where the fluorescence laser would make them to illuminate for 2 weeks to image. And this will increase the resolution because the size of this hole can be very small. And this, if we had 200 nanometer here, with a STED laser or STED system, you can have practically around 70 nanometers because the size of the hole in the middle of the donut depends on the energy of the laser that illuminates the donut. And if the energy is too high, you simply kill your sample. That's low. So there is a limit. If you illuminate a diamond crystal, which doesn't care about the heat, then you can make the resolution of the STED microscope to 2 nanometers. So this means that again, in lateral resolution you don't improve much, but in axial resolution you don't improve much unless you combine it with the second donut. But in lateral you get it around this.
And if it's placed on this graph here, where would the range be if it's supposed to be in this graph?
Basically, it's hard to place it there, yeah, because the role of the pinhole is replaced by, so in terms of the Z resolution, it depends on the actual pinhole setting. So you put it wherever the curve shows you, but on the lateral resolution, you are on a different category completely because of the X action. But otherwise, in terms of the light path, it's an addition to a focal microscope. It's not a separate system. Yeah. So the pinhole setting would reflect what the focal system in general reflects, but laterally you are doing much better. It's actually a very interesting question because what we have been receiving lately from research groups from the university is exactly a combination of confocal images and STED images. Because in STED microscopy, the resolution is so high, and this is also a problem with single molecule localization microscopy techniques like Storm, that you may not see the actual structure. So let's say you are imaging actin fibers, and with super resolution microscopy, you will see the structural details, the groups of molecules, but you may not see the whole fiber. Or you have polymer molecules, supramolecular structures. With STED, you don't see the structure anymore. You see the substructure. And then you need a confocal image to know where you are. So then what you do is it's the same microscope anyway. So you take an image in confocal mode and you take an image instead on the same sample, you don't move anything, you switch a button. And then when the image comes to you, you use the confocal images as a mask to know where you are. Where is the supramolecular polymer, where is the actin fiber, and so on and so forth. And then based on this mask, now you go to the STED microscope image, for the STED image, and now you know, okay, I'm within this fiber. What does my actual structure look like? And where does the fiber and where does the fiber start? In the STED, you will not see. And it's even worse with like I said, with Storm and on. But you really need a wide field image at least to know it. And so it's a usually it's combined. LIGO, for example, has this special format, LIF format, where you combine the confocal at various wavelengths and the STED at various wavelengths in one file. And then you put this into JIPipe in this case, and then you separate the channels and then you know. Okay. Anything else? Yeah.
Maybe could you comment on the upper microscope from Zeiss?
Yes. The other, we have too little time here, unfortunately, but if you guys have a bit of patience, there is such a thing as structured illumination microscope. It basically means that if you have a wide field microscope where you would have a light source, just a halogen lamp, for example, and or laser doesn't matter, and you illuminate your sample, you get a fluorescent image or you get a clustered plasma. Now, if you, instead of using the homogeneous illumination field, you use a pattern illumination field. Let's say a grid like these lines. Instead of having one homogeneous field, I would use a grid. Bright, dark, bright, dark, bright, dark. And I illuminate my sample. Of course, then what do I get? I get a stripe image. So what I have to do is I have to move this pattern at least as much as the distance between two bright lines to get a full illumination. Well, I have then as many images as the number of scans, and each of them are striped. So this has the advantage that with a little bit of mathematics, combining these, let's say, 6 images into one, I can get a simulated confocal image. Well, I can eliminate the out of focus signal, most of it, of the out of focus signal. The idea is that if you have you guys ever seen a Moiré pattern where you have two grids and you rotate them relative to each other and then it starts to reveal periodic patterns at a much larger scale. You can Google it. This basically means that if I have two periodic structures and I Google it, the two patterns will result in a new pattern with a much larger size. And if I know at least the pattern of one of these, like how far are the lines, for example, and I know what the result of the overlap is, I can calculate the other one. But the idea is that if I have a biological sample, which has a distribution of molecules, and I illuminate this with a pattern illumination, I will get, it's not an interference, but a combination signal, which is also periodic, but at a much larger period. So I can, let's say I have molecules which are 100 nanometers long. And then I illuminate this with this pattern and I make my calculations. I can make this pattern, instead of being 100 nanometer cycle size, 300 nanometer cycle size. So 300 nanometers is now above my resolution, so I can see it. So I converted a 100 nanometer sample periodicity into 300 nanometers so I can see it. And since I know what I see and I know what I illuminate with, I can calculate the image. And that's how aperture works. It uses a pattern illumination, it's usually a grid, and this grid is moved across the sample and also sometimes rotated. So I get 6, 12, whatever images, which are all patterned, but from that, with very simple mathematics, we can calculate the high resolution. So this is a cheap confocal dish system. And that's for the aperture. It's produced by size, but originally this was developed by a group in Rochester, New York, back in 1994, 95. And I know this because the group I worked with then in Baltimore was involved in analyzing these. So that's why I know these people. Of how to get, because there are always artifacts when you illuminate with the pattern illumination. You get harmonics like twice or three times the frequency you have to illuminate. The point being is that it's basically a microscope with a pattern illumination, much cheaper. I don't know how much one is these days, but it gives you good enough quality so you can do 3D image analysis without having a confocal microscope, and it's fast. It's a wide-element system, it's a camera-based system, so you don't need to scan. Confocal microscopes are slow. Spinning this confocal is faster. But point scan confocals are slow, and these guys are much faster, cheaper, gentler. So usually structured illumination microscopy with gentle is something and fast, and it doesn't need special vehicles. So since we only have 3 hours, we could only cover the basics and the confocal, but in the other 3 hours, you could go through these super resolution techniques, but but yeah, if you have questions, just ask and you can get these answers online. But based on this, you should also understand how these things work. Anything else? Anybody needs that class? Oh, yeah. Very good. We have enough over it. Do you guys have like 5 minutes? Or if you raise your hands again so I can count. 1, 2, 3, 4, 5, 6, 7. Is that 7? Can someone check? Maybe 7. Okay. Then,
I'm not sure. I need to check if I can do it.
so that's 8. That's enough. So you don't have to stay. You can go eat. Folk should walk it. We have 3 or 4 and we can make more. We need time to set up the laptops anyway. And Lumen said we have some time. So we told you a little bit about super resolution. Yeah, I put some slides together in the last 10 minutes or so. And we quickly go through some basics. So you learn a little bit more. Totaling the diffraction. I mentioned this in the morning class. This is sort of kind of a super resolution method in the sense that it gives you a very fine Z slice. It does not increase the resolution laterally, but it does axially. Why does it do that? You remember total internal reflection. And I also said when you are above the critical level, you have total reflection, but that's not true actually. What happens is that some of the light wave will propagate into the secondary medium. Not much of it, not deep. Maybe 100 nanometers, 200 nanometers or so. So basically what happens is that unlike using a regular perpendicular light beam, if I go at an angle, then in this layer here, the light, the electromagnetic wave will penetrate into the other medium, just a little bit. So it will illuminate, for example, in this case, the very bottom of the cell. You will see the membrane, for example. You will see if you label membrane lipids, for example, you can see that. And basically, this layer is in the order of magnitude of 100 nanometers. And you don't have to do anything to generate it. You just have to set up the illumination so it's above the critical angle. So this way, if you have a regular fluorescent microscope and you buy a so-called TURF lens, total internal reflection microscopy lens, this lens allows you to illuminate at an angle rather than perpendicularly. If you set this up, then you will have on your microscope for free 100 nanometer axial resolution. Now, by itself, this is only useful when you have interesting events happening at the bottom of the cell, in the membrane, for example. You can see actin filaments, you can see cytoskeletal movements, you can see motor proteins moving along the membrane. How deep you can see it? Well, it depends on the angle, but it also depends on the intensity of the lighting. So, for example, if the incidence angle increases, then the depth at which you get the penetration decreases. So you can, to some extent, control how much you see in the axial direction. On the other hand, the intensity very quickly drops off. So in this case, if you look at the relative scale, at 100 nanometer penetration depth, we still have about 70% or so, but at 200, we basically have no impact. So that automatically limits the penetration depth to, like I said, about 100 nanometers. Now, what this helps you with is that if you see in a wide field microscopy image, just a blurred image, in your TURF image, you will see this 100 nanometer layer. So, like I said, for example, the membrane or motor proteins, etc., can be observed. Oops. This somehow. There we go. Okay. And this is a video of the same, so you can see events at a very high resolution in terms of the axial. The lateral resolution is the same as we learned from the daily criteria, so there's no change there. You see the nuclei during the video, and you can also realize that because of the relatively low intensity, this is very harmless for the cells, very gentle for the cells. So you can have long-term live cell microscopy imaging carried out. Like see here, it's 85 hours long, so it's very gentle on the tissue and on the cells, but you don't see anything above 100 nanometer flow. How is this then set up? You basically have your specimen sitting on the cover slip. You illuminate this time at an angle, not perpendicularly, and then you basically realize illumination from this thin layer. What we usually use here as an illumination source is lasers. The alignment is not trivial because you have to set up the angle, the laser beam at an angle. So basically, during the setup or the alignment, there is an open laser beam in the lab. So this is not done in the presence of microscope users. It's not allowed to be done by anybody else except the microscope manager, him or herself. On the other hand, it does not require any other perforation. So any dye that you want to use can be used just like you would in fluorescence microscopy. Some of the methods in super resolution do require special labels. This one does not. And what I wanted to add is that sometimes the most useful application of curve is not by itself, but in combination with other super resolution methods. And why this is important is that you will see in a minute is that many of these methods, for example, STEP, unless you have a second donut, an axial donut only increases resolution lateral, not axial. But if you combine it with TÜV, you immediately get a very high axial resolution. For a thin layer, yes, but still it is usable. The most popular one that you guys will most likely encounter is STEM microscopy, simulated emission microscopy. What does it mean and how was this discovered? And we briefly talked about it before lunch, but this was really just a bit of a verbal introduction. It was developed by Stefan Hell and Jan Wichmann from here in Germany, and they did get a Nobel Prize for it 12 years ago. It was a big buzz in those days. The first STEM microscope became available, when was that, 2008, I would say, 9, something like that. And then we had one of the very first ones in the core facility in Cambridge, I remember that. So 2009, I would say. And then after it became how useful this is, they got a Nobel. So I remember for several years, people were waiting for the news from the Nobel Prize Committee of whether they finally received the prize or not, and then it happened. And to understand how this works, we have to remember how the rating criterion of resolution is set up. As I mentioned in the morning, the definition here is that there has to be a 20% intensity drop between the two peaks in order for the human eye to see them as true. This means that when the two objects are too close to each other and the point spread function is wide enough so that they overlap here, we will not be able to resolve the two objects. This is what we talked about in the morning. If I move them farther apart, I start seeing them. If they are so far apart that the two airy maxima do not overlap, and I see them as two. If they touch, then I am on the borderline, and if they are overlapping, then I do not see them as two objects. And we also talked about the fact that the reason, or to make this better, would be, for example, to have this signal thinner. And this means that the point spread function should be smaller, should be thinner. And you remember in one of the slides we discussed, for example, how the point spread function, that is basically the shape of the end pattern, will change if I increase the numerical aperture of the lens. You remember it was 0.2 all the way to 1.3. The size of the point spread function very dramatically decreased. So with higher NA, you have higher resolution, a smaller point spread function. But to resolve an object, there are 2 point spread functions that you have to consider: the excitation side and the emission side. If either is wide or poor, then your resolution goes. If you are both thin, then your resolution is maximized. If you maximize one of them and then the other one remains as unresolved or as the natural diffraction limited, then you get a super resolution method from either the excitation side or for the emission side. Instead, we are starting to manipulate the excitation side. That is, I'm trying to make the width, to put it simply, the width of the illumination spot smaller. I'm not worried about the emission side at the moment. I'm just trying to worry about the excitation. How do we do that? Well, I cannot make the laser spot smaller than a certain limit because of the diffraction. Laser spots are just as much subject of the law of diffraction as anything else. So focusing the laser spot to a smaller one is not going to work. Eventually we start to see diffraction. So somehow I should try to limit the size of the active laser spot, the laser spot that actually activates molecules to fluoresce, as small as possible without actually trying to make the spot itself small. And for that we use two lasers. One at a much higher wavelength, basically an orange colored laser, which forms not a spot but a dot. The middle of that is the torus. This is a high energy laser, and I align that very precisely with the laser that I would use anyway for my fluorescence excitation. So I combine two lasers. Technically, this is of course not easy because if any misalignment will ruin the effect. But if this is set up properly, then from a laser spot, which is again diffraction, so I cannot make this orange donut smaller than it when a few couple of hundred nanometers. But what I can do is, if I increase the energy of the orange laser, I can make the spot in the middle smaller. Now, this means that overlapping this, there is a diffraction limited that is full-size green laser spot. But the actual excitation of the green laser happens only in the center. Now, why is that? It is because this orange laser will have a funny effect on the fluorescent molecules. It will excite them, and it will force their electrons to come down. This is the orange line here, at a relatively small energy gap. Now, small energy gap means less energy, lower frequency of the photon, higher wavelength. So the photon that comes out from this so-called stimulated diffraction is a red photon. So the energy doesn't do anything, it's there, it's preserved, but it comes in form of a red photon. I can easily filter that out. So this means that all the molecules which were illuminated by this orange donut will be excited and then decided or relaxed, forced to relax. So as a result, what I see in my image as I scan through my sample, it's a confocal scanning, laser scanning confocal. Only those molecules which were not hit by the orange donut. So in fact, I will only see fluorescence in the proper fluorescence range from here. So regular beam, depletion beam, they are all diffraction limited, but the effective excitation will only come from here. So if I look at my spectra in cross section, then this is what it looks like. And my effective point spread function is now this. So from this point spread function, I went to that on the excitation. I did not touch the emission side. I'm still happy what I have. So when I compare the actual point spread functions, the excitation side one, I go from the diffraction limited confocal to the stat limited, much smaller point spread. The system is fairly straightforward, except for the alignment. You need an orange laser, you need your regular blue, green, whatever excitation laser. You align them properly, and then you scan the sample. This has to be scanned. It's a scanning microscope. So basically, you are superimposing the original PSF and the donut generated PSF, and you end up with a much smaller point spectrum. This is the layout, the two lasers, dichroic mirrors, the lasers are aligned, and then with this small spot, we scan through the sample. Now, why does this work? It works because with the regular confocal, when you illuminate the sample, you get a 1 micron area, all of these molecules will be excited. So what the signal I will get is this big. That is, I cannot anymore resolve how many molecules there are behind that. But if I use the STED layout, I'm only actually getting signals from these few. These orange ones are all depleted, and now I get a much smaller area. In fact, otherwise it's built on a regular laser scanning confocal microscope. It's an addition to it to generate the overlapping two lasers. This has a little bit of optical trick to make the donut-shaped laser beam. It has been known actually since the 60s how to make such a donut-shaped beam, so it's not a new principle. And then, once you have the layout, you simply scan through the sample, and you get your super resolution. One critical burst. Now, the size of the hole in the middle of the donut, as I mentioned in the morning, gets smaller as the energy of the orange donut gets higher, but that eventually starts hardening the sample. So whilst the theoretical limit is in the nanometer range, the practical limit in biological samples is about 70 nanometers. This compares with 200 nanometers in the confocal laser, so you are still doing very well. And like I also mentioned, typically when you get images from a confocal STED microscope, you get a combination of confocal images and STED images of the same area, so that you can use the confocal image to know where you are and see a complete image. And then you use the STED channels to resolve details which you cannot see with the confocal resolution. This is now your resulting PSF. And then as you scan through, you will get with the regular laser just two spots combined together. But when you decrease your excitation point spread function, now you will get two different spots. So this dip is now definitely below above 20%. So you will see that as two separate spots. The resolution of the microscope depends on the intensity of the orange laser, as I mentioned. It's on a square root function, so it's not as sensitive as you would maybe hope. So this curve is fairly flat. And it also shows you that above a certain energy level, you don't gain too much resolution anymore. The main gain is in this range. Then the curve flattens out. So if you go above this intensity, this energy density, around 40 nanometers maybe, you don't gain much more by increasing the laser power, but you will harm the sample much. So that's why the practical limit is somewhere in this range, where a regular STED microscope can be practically used. The best resolution is around the nanometer range. That's, like I said earlier, the diamond crystals, which more lines, the heat coming from the orange laser. In optical, in the biological samples, it's nowhere near that. But the difference is actually thematic. You can resolve structures, for example, membrane nuclear pores, which you do not see in confocal microscopy images. So this is what happens when you try to decrease the point spread function on the excitations. But there is also the emission side. What if I use regular excitation, but I try to make the point spread function of the emitted light? the emitted light path. What does that mean? Well, it means basically that whilst I know that the size of the spot that comes from a single molecule is still diffraction is limited to around 200 nanometers. If I somehow could make sure that my molecules do not flash at the same time if they are close to each other, then whilst I would still see these relatively large spots, 200 nanometers or so, but if there were so few of them that they are separate from each other, I would still be able to tell where the molecule is with a very high precision, because they would be in the center of this distribution. So how do I do that? How do I get these molecules to not to flash at the same time? There are various methods. I only will talk about one. But in general, they are called single molecule localization microscopy, or SMLM, as a collective name. And the idea is exactly that we somehow, one way or the other, force molecules that after excitation with the fluorescent excitation laser, they do not emit photons, they do not go back to their ground energy state at the same time, but rather they come back slowly and gradually. And what happens if you do that? Well, if I see one molecule and I record the fluorescent image of one molecule which is sitting by itself, no neighbors, nobody is flashing, everybody is dark, then I can detect this distribution of intensity from the molecule, and I can increase my pixel resolution, so I can increase my pixel size, so that I can resolve this very nicely. And I have this Gaussian-like curve. And I know that it's only one molecule behind this. So can I now tell with very high precision where the molecule is? I can, because if I fit this curve on it, it's at the peak of this curve. So this means that by recording molecules flashing singularly, I will get these individual spots, and they are all big. They are all diffraction, but they are far from each other. So if I keep taking images, and in each image I only have a few molecules flashing, at the end I will have the whole sample resolved at high resolution. Now, how many images do I need to get this image? A lot, thousands. So this is not a fast method. If I want to make it fast, and by that more molecules flash at the same time, my resolution will drop because they start to overlap. And I have to throw those away, or I have to use more math to say, okay, this is probably two Gaussian, so I'm going to fit them together, and I try to estimate. So your reliability will drop with that. But if you do this carefully and patiently, then this takes you up to 10,000 images or so to get the whole image. But it does work. And it doesn't need anything much except for a high sensitivity camera, a dye which, when illuminated with, for example, a UV laser, excites the molecules, and then the molecules come back very slowly. And patience, a lot of patience. Live imaging is difficult because by the time you collect enough images, this method, the cells may move on. And then you will not know whether the new spots that you see in the next image are more molecules or did the cells simply move on. How good is the resolution? Well, it depends on how many photons I detect. And now I go back to what I told you in the morning. We need more photons. Because to fit this three-dimensional Gaussian, which is the most difficult way to fit this, to fit this 3D Gaussian, the higher the intensity, the better the fit, and vice versa. So if I have 100 photons coming in, my fit will be so poor that the estimated location of the peak, where the fitted curve peaks, will drop. It will become a very wide range. So how do I define the resolution of a localization microscope? Well, it's simply the width of the Gaussian distribution, the full width hardness. Now, how do I improve the full width hardness? Again, with more photons. So the goal will be molecules which can be put into a state where they come back slowly from the excited state to the relaxed state. So they emit photons spatially separately, but they emit enough of them. So the signal from each molecule is bright enough so I can fit a very nice Gaussian function. Of course, it also helps if you have a very good camera, high sensitivity. It doesn't have to be terribly fast, but it has to be very high sensitivity. And then you end up with images like that, where the individual molecules is laid out with these spots. Now, if you start to have clusters, because either your chemical structure was wrong or because you illuminated the tissue with too much laser on the way back, you will have clusters which will then drop your resolution because there is not a whole lot you can do with this. Again, you can have a model and run it and try to estimate how many molecules there are there and where they are, but it becomes more and more difficult. So the best is if you have single spots, single molecules, and then you fit your Gaussians on it, and then you get your high resolution. Typically, again, this has to be combined with wide field fluorescence microscopy. Otherwise, from this pointillistic image, you don't know where you are, for sure. So you need a lower resolution image, and that's typically just a wide field fluorescence. What kind of labels you can use? Well, you can use fluorescent proteins. You can use synthetic dyes. So these are expressed by the cells. Synthetic dyes, which you just add to the sample. And then you can also use solid-state devices, so-called quantum dots, which are very, very tiny molecule-size dots made of semiconductors, where by building these shells properly, you simulate a molecule in the sense that this structure can be illuminated and that it will have electrons excited and then electrons coming back and emitting photons. So this is a simulated fluorescent molecule. The advantage of this is that the optical properties are entirely which wavelengths range will excite, which wavelength range will emit, how long the electron will stay in the excited state, and so on. These have to be tagged so they go to the proper molecule that we want to examine. Okay, so this is what we do. We have two molecules close to each other. I cannot see them separately, but now I force them to blink, either this one or that one. So at the end, when I do my fit, I will get the proper distribution, and at the end I have my high resolution. What resolution are we talking about here? I would say 10 to 20. Again, the higher the signal, the better the fit. The problem is, of course, that this is really two-dimensional. Typically combined with Deutsche illumination, so the total embedded refraction will limit that naturally to 100 nanometers or so I don't get out of focus images. But what if I want to actually have a 3D image? But 3D here means maybe a micrometer. We're not talking about 50 microns, that stack. We're talking about 1 micrometer. That stacks at 20 nanometer resolution. How do I do that? Well, here we take advantage of one of the aberrations that I talked to you in the morning, astigmatism. Astigmatism, we remember, is the dependence of the focus point on the polarization angle of the light. So what I do is I put an extra lens in the light path, a cylindrical one, which will purposely ruin the image in the sense that it introduces astigmatism. Because of that, my point spread function will start to shift along the z-axis. That's what astigmatism does. So this way, you can, by positioning the stance there, to get a signal in approximately, in this case, 800 nanometer range. So as I mentioned, approximately a micron thick layer. And if you have only 20 nanometer step size, then you have a 50 layer 1 micron thick Z stack. So we are talking about very, very small structures, individual molecules. Again, the diffraction limit is still there, so the individual spots are as they are, within the diffraction. But our measured fitted point spread function will be much narrower. So now we see a method where the emission side point spread function was manipulated. Can I do further? Yes, you can combine excitation side instead with emissions. There are many combination methods where one or the other methodology or method is combined with some of the others. And one of the most popular ones is the structured illumination microscopy. And that this is just a summary. Oh yeah, I wanted to talk to you about very, very briefly. How do we plot the results of a localization microscopy image? We can just put dots there where the center of the Gaussian function, but that's really difficult to see. The other option is you simply draw the Gaussian itself that you fit it. That's often used. The other option is you just plot a two-dimensional histogram of the density distribution, and you replace the dots with that. And then you end up with images where you actually can recognize structures, especially when you overlay it with a wide field microscopy. And then for the segmentation, you have your raw signal, and then you will learn tomorrow and Wednesday. You set up a threshold, so you separate the foreground from the background. Then you segment them, and once you have the segmented areas, then you can say, okay, the smaller ones of which I have the most, these are single molecules. The ones which are approximately twice the area, they are probably 2 molecules, and so on and so forth. And from this one, then you can have a size distribution. You can have an estimated number of molecules, even without dropping out the larger ones, because you can estimate how many molecules there are. Okay, in terms of the fitting, typically it's a Gaussian function. Of course, in XY you use a two-dimensional Gaussian, which you can simply put on your GPU and then do a very quick calculation. So the modern GPU, this actually is an almost live method where you can actually monitor the molecules as they flash and feed them basically online. If you have an astigmatic lens, as I showed you, then it becomes a three-dimensional Gaussian, but the basic principle is the same. It's just one dimension, one more extension to fit, and this can again be programmed easily and carried out at a high speed. And of course, if you have more than one molecule, which is the most common thing, then you very simply add together the functions that you fit. So in 2 or 3 molecule types, we have 2 or 3 point spread functions linearly added. Very good. And finally, the simplest method, which includes upper tone, which our friend asked us about. Now we renovate. Structured illumination microscopy, by far the cheapest, simplest, but it limits your resolution increase by 2. The maximum resolution increase you will get already theoretically is 2-fold, unless you combine it with, for example, high resolution, for example, stat image. Here is the principle, and now I can a little bit more deeply explain what I started to explain in the morning. When I look at an image, for example, I picked here periodic images, like a striped muscle fiber. When I look at these images, I can convert this into a so-called frequency space. Frequency here means how far the various spatial components are from each other inverted. So for example, if two objects are 1 micrometer apart, then their spatial frequency is 1 divided by 1 micrometer, so it's 10 to the minus 6, so it's 1 meter. So I can take my images and I can plot the image instead of showing the intensity by showing the inverse of the distance between the nearby objects. And then I get the so-called Fourier transform, that is a frequency image of the frequency presentation. The bright spots here correspond to the most frequently appearing distances in the original image. So for example, in this image, the frequency at which these stripes occur is very high. So the dark and bright lines, or the nearing, or the most nearby bright lines, are very close to each other. So if I calculate the distance between two bright lines and calculate the inverse, that's a high number. In this image, it's a low number because they are far from each other. So if I put this plot up here, then images which correspond to this large spatial distance will be represented by low spatial frequencies. So in this image, this will appear here. On the other hand, the most frequent these lines, the closer they are, so their spatial frequency is higher. So this image will appear here. This bright spot will correspond to that image. This image will be represented by this frequency. Why is it important? It's important, without going into theory, is that an optical lens, which we talked about in the beginning, when it forms an image of an object, it generates the Fourier transform of the object. Basically, it's a super fast computer with which you can do Fourier transformation analog. It's actually being done. So what that means is that at the back focal plane of the lens, where the image is being formed, the size of this frequency space determines how high spatial frequencies we can let through the optical system. Now, unfortunately, just to show you where these things are. So the high frequency ones appear here. So if I take the Fourier image and I did this just in ImageJ, you manually delete this high peak, and then you invert the Fourier image into this irregular space image or stem space, this frequency is gone. Yeah. And then I delete this one, then this is gone. And then this is gone. And then this is gone. So at the end, you have nothing left. So this means that if my microscope does not let this entire range through, then the high frequencies I will not see it. Which means that by eliminating, for example, this peak, I will get rid of this frequency and anything higher. And unfortunately, that's what the microscope does. It limits the spatial frequency that can get through the objective. This is the Fourier transform of the original image, and the yellow circle shows you what the lens will let through. So all the spatial frequencies here are not going through, which means that objects which are so close to each other that their spatial frequency reaches here are not seen anymore by the microscope. This is the resolution limit. The microscope cuts off the spatial frequencies at a certain range. The higher the NA, numerical aperture, the larger the circle. The smaller the point square function, the larger the circle. You will now also understand that there is a correlation between this area, which is called the optical transfer function. This is how much frequency goes through, transfers through a microscope, between the optical transfer function and the point square function. They are each other's Fourier transform. Point square functions are in geometrical space. Optical transfer functions are their sisters in frequency space. So if I know my point square function, I will apply Fourier transform on it. You put it into image chain, you put it into Python, whatever. It will calculate for you the optical transfer function. And then you draw this over the Fourier transform of any image that you just collect on your microscope. You will get this yellow circle and you will know where the frequency cutoff is. And this is how you deal with optical resolution. Now, there comes a trick which I told you about. Why? Can I somehow get these higher frequency peaks closer to the center? I can. If I illuminate the sample not with a homogeneous field, but with a pattern field. A pattern field will give you a very strong Fourier transform peak at the spatial frequency of the pattern itself. The finer the pattern, the higher the frequency, the better the effect. And what basically this means in a very primitive way is that if I have two structured patterns and I overlay them either with a shift or a rotation, I will see the appearance of the so-called Moiré pattern, which is the overlay between two structured images or two structured light fields, which means that if I have an image, I have a sample which has objects which are beyond my optical resolution, why don't I, instead of illuminating the laser spot, extend my lasers and put it into, or use a regular lamp or a diode, and cut it into a pattern light field. Make it like that. And illuminate the sample. That will generate a Moiré. This basically means that if I take this illumination pattern and I have these samples which I drew before, and this, you saw that these two, you're already outside the yellow circle. They were not resolved by the microscope. But now if I illuminate these guys with such a light field, this is what I will get. This is from that, this is from that, you understand. This is from that. What you see now is that from this very fine pattern, I have a much more coarse pattern because I illuminated it with one of these fields. This one is as low spatial frequency as this. So I can see in the microscope. And I didn't change anything, I didn't have to lower the special light, I didn't have to do anything. All I had to do, make a periodically transparent foil or a piece of metal or whatever, and illuminate my sample with that. I generate a Moiré pattern, and now if I put this through the microscope, I can see it. So what did I do? I grabbed these maxima. This is the pattern of the illumination. As you see, the maximal lines are at an angle because the pattern itself is here. But what I do is I apply this illumination to the microscope, and this will then shift the optical transfer function of the microscope. So now what happens is that when I illuminate the sample like that, then the two maxima, which were, remember, out here, now they are at an angle inside the yellow circle. What did I do? I made the invisible visible by shifting their spatial frequency to a lower value by illuminating the vertical. And this is the principle of structured illumination microscopy. It's very, very simple. Like I said, in 94, we already had a system like this. And from this one, this basically means that you didn't change the optical transfer function, but you changed the frequency spectrum of the sample. And of course, the individual images, like I said at lunchtime, they are patterned. So the pattern illumination has to be shifted or rotated or both to cover the whole sample. But what you get at the end is, instead of that, you get a twice as good resolution of the image. The maximum that you gain is, like I said, twofold. There is no reason why you couldn't do two-dimensional or three-dimensional or time series. This is a confocal image. This is a single image. So you get, like I said, approximately twofold resolution. Upper tone systems, which are very frequently found in clinics, research institutes, etc. Like I said, they have a cheap version of the confocal microscope. They are built exactly like that. They use an illumination light source diodes, for example. They use a pattern in the light path and they shift and rotate. Pattern is up to you, how many shifts, how many rotations, how much should it shift between steps, and so on and so forth. And with very simple mathematics, for example, you can get the maximum intensity projection and calculate the minimum intensity projection and subtract the second from the first. It's simple way. Will give you the image that you see here. This can be combined with other techniques, for example, two-photon microscopy, line scan, STED, etc. So you can increase the resolution.